Hello, everyone. We are starting our showcase session. We have 6 great talks today, showcases, each one of them about 30 minutes long. So the way we'll go, it's about 20 to 25 minutes. The speakers will have the microphone, and then we have like 5 to 10 minutes maximum, the Q&A. So if you do have a question, please press this ask a question button and post your question. And the speakers will take the questions at the end of their session from this list. So it is my pleasure to introduce the first showcase with Dr. Jamie Knight and Dr. Thomas Novotny. They are presenting on GPU-enhanced neural networks. And Jamie and Thomas, you have the microphone.
Thank you very much, Anka. So I will start with a very brief introduction to what this is all about and about GeNN. And then Jamie will take over and do some of my interactive part showing how GeNN works in an IPython notebook on a specific example. So just to cut to the chase right away, what is GeNN for and what problem is it solving? It is generally difficult to map spiking neural networks to GPUs. And the main problem is that to make it efficient and run efficiently on GPUs, you need to engage with this model how GPUs are programmed in terms of grids of blocks and warps and so on. And spiking neural networks don't come in that shape. So you have to do a lot of bean counting and organizing of code to fit one into the other. And because that's difficult for the programmer and the scientist specifically, we have invented GeNN, and the approach of GeNN is basically to be a minimal meta compiler that takes care of all that bean counting. And then it generates you these kernel functions that run on the GPU efficiently and convenience function for shifting data around, and all the rest is up to the user, the scientists who want to investigate spiking neural networks. And just to show you how that has developed over the years, we now have this kind of ecosystem around GeNN where we have Python interfaces, interface to other simulators like Brine 2 and Spine Creator. And in the middle sits this kind of GeNN meta compiler, and then we have backends for efficient compilation. So we used to have just Cuda, and now we also have OpenCL. But I won't delve into any details here. If you're more interested in these things, you can read it up in our recent publications. Just to show then a couple of numbers here. A recent benchmark we have done was done on this cortical microcircuit model, which represents about 1 square millimeter of rat cortex with 80,000 live neurons. And what we found was that with different GPUs, of course, you get different speeds. So here is execution time for different hardware, from embedded systems that are credit card size to powerful workstations. And we found that we can simulate faster than real time in the most recent iteration of this, and about as fast as you can do on the fastest instantiation with Nest, and a bit faster than Spinnaker that runs in real time these days. Okay, so much about the GeNN in general. And then I wanted to very briefly introduce the model Jamie is going to talk about. Going back to the 1960s work of Thomas Cowan and others, we know that classification works better if you project the patterns to be classified into higher dimensional spaces. And the whole idea of that is that it's hard if you have a linear classifier, which corresponds to separating points with lines. In a situation like this, you cannot find a line that separates green from blue, but if you go into a higher dimensional space, you can find a plane that separates them easily. And this kind of idea, many people have caught up to this, but also I myself have dipped my toe into this a while ago, seems to resonate with how brains are organized in many different species, where here in the case of insects, we often see this kind of convergent, divergent, convergent pattern of connectivity in the brain. And the idea would there's some sort of encoding of patterns to be recognized, classified, and there's this expansion. So this is the original classification space, and there's this expansion to a higher dimensional space that then makes it easy to do it. And that's the kind of model Jamie's going to show you how it works in GeNN, and he will demonstrate how GeNN works and how this model works. And two things that he will demonstrate on the way is that this needs a sparse code, and that's something we've shown theoretically, and it's been observed experimentally in locusts. And the other thing is it needs stable sparse codes, and they don't come naturally with this expansion from one layer to the next. So if you don't do something extra, you get this kind of activity, which is very unregulated. So you get different number of spikes given different input patterns, and then you need to regulate it by some sort of feedback or feed-forward gain control, and then you get something more regulated. And you see the same thing in the experiments, that there exists a neuron that does that. This is in locusts. Similar things have been observed in flies. And so Jamie will, on the way, introduce these concepts as well when he's talking about building the model. And I'll leave it there. Here's the diagram of the model, but Jamie is going to explain step by step how you build that in GeNN and what kind of results you observe. So over to you, Jamie. You're still muted. Jamie, you're still muted.
Okay, thank you, Thomas. Okay, I will just share my screen and we can begin. Okay, can someone confirm that they can see my IPython notebook?
We see it. We see
Fantastic. It. So I'm going to build this model up kind of layer by layer in IPython and hopefully give you an idea of what the experience of using GeNN might be. If you go to the Sched page for this talk, there's links to these notebooks and the training data and weights that we train as part of this. So we're probably going to go a little bit fast for people to kind of keep up live, but hopefully you'll be able to have a go afterwards yourself if you're interested. So like with Python scripts, we start by importing a bunch of standard modules for plotting and numeric processing and stuff, as well as these two PyGen modules. So for convenience, we've converted the MNIST dataset into NumPy format rather than this like strange arcane binary format it tends to come in. And as part of this process, we've also normalized it. So just to demonstrate that, so we check that the sum of each image is 1. So this is the first step towards making sure we get a nice stable sparse code, is that the sum of the input going to projection neurons is 1. And as you expect, the MNIST digits look like MNIST digits. So something hasn't gone too deeply awry. So at this point, the model's only got a few hyperparameters. So first of all, we're using a 0.1 millisecond time step. Fairly arbitrarily, we're multiplying the input images from MNIST by 80 to get a current that does something meaningful to a standard lift neuron. And because we've got 28 by 28 MNIST pixels, we've got 784 projection neurons. And we choose to present each stimuli to the model for 20 milliseconds. Here we've got a standard set of lift parameters. So this is a pretty normal lift neuron. It's got a relatively short refractory time. Normal model. So we're going to use this for almost all the populations in our model, but for these projection neurons, to get this code sort of looking the way we want it, we just increase the refractory time. So each neuron will only spike once in each trial. And in order to apply the MNIST digit to these neurons, we use what's called a current source model. In GeNN, this is just a kind of easy way of adding input to a neuron model. So if you don't want to rewrite the neuron model with some kind of input processing, you can add a current source. So in this case, it's pretty minimal current source. So it's got a state variable called magnitude, and the injection code gets run every time step. And all that does is just inject a current of this magnitude into the neuron. So this means we can change the state variable from our code and change the current going to the neuron very easily. So we start to build our model. So first of all, we create a GeNN model object. This first parameter here, this float, is the kind of precision of the model. So this is kind of the data type of state variables. So in this case, they're 32-bit float. You can use double precision if you want to, but for this, it's most definitely not necessary. We then set the model's simulation time step to this dt value, and we set a fixed seed. We want to do this because we've got this random finite connectivity, which we're going to add later, and we want this to be the same every time we instantiate the model, especially between testing and training. Amusingly, we got this wrong, and between us, me and Thomas spent several days trying to figure out why this model did very little, and that was the reason. So we've set the parameters for the lift model. So now we want to set the initial state of the state variables. So we initialize its voltage to the reset voltage, and we put it in out of its refractory time, which just means setting that to 0. And then we add a population of these neurons with the correct number, so 784, to the model. And we turn on spike recording so we can see what they're doing. And then we add this current source to the model. So we now run the code generator. So that's built the model, built the code, and then it's loaded the code into Python. And here we're setting that we want to be recording for the present time step. So this basically means you've got a buffer of this many time steps of recording data that you can easily access, which in our case aligns to the number to each stimuli. So now for this stage, we're just going to show the first 4 endless digits to the model. So we loop through these stimuli. We copy the training image times this input scale into the current source, and we push this to the device. So one thing with GeNN is you have to manually manage the transferring of data between the GPU and the CPU. So this is sort of uploading from the CPU to the GPU. And then we loop through these present time steps, and we step time, which just advances the model by one time step. Then, so with these classification models, you've got 2 options. You can kind of leave the model after you present the stimuli for a long time for the dynamics to settle, but that tends to mean you have to simulate for a long time. So instead, we just reset the neurons manually. So in this case, we pass the values we initialize the state variables to, and we set the model variables back to that, and we re-upload them to the device. So that will reset the neurons back to a default state. Then we download the spike recording from the device, and then we plot the results in Matplotlib. So here you can see our 4 stimuli. You can see a nice kind of sparse spike patterns. They're obviously all relatively different. Most of the spikes happen early in the 20 milliseconds, but there's some kind of dragging out. So this first layer looks promising. Now we're going to go on to the second layer where we start adding the GeNN cells. So this notebook starts off like a copy of the other one. So we're adding a few more parameters. We're adding number of GeNN cells. We're using 20,000 here. And we're specifying some weights for the fixed connections between the projection neurons and the GeNN cells. And we're going to be using exponential synapses here, so we've got a time constant for these 2. And finally, we've got this fan-in. So this is how many projection neurons are connected to each GeNN cell. So each GeNN cell is connected to 20 projection neurons. We make our current source again. And here we just add this second neuron population. So we add the GeNN cells, again, in this case, just using the standard lift parameters. We turn on the spike recording for that. And then finally, we add this new synapse projection between the projection neurons and the GeNN cells. So there's quite a lot of stuff going on in this call. So this sparse global G, first of all, this means that the sparse bit means that this connectivity is sparse, so it's stored as a sparse matrix. And the global G means that the weights are shared between all of the synapses, so you don't have to store individual weights, which saves you potentially a lot of memory. It's got no synaptic delays. This model we haven't included any. And there's 2 parts to the configuration. There's what we call the weight update model, which is where you kind of specify learning or anything like that might happen on the synapse. In this case, there's no learning. You've just got static pulse, which is kind of the most simple spike-based synapse type, and we just specify the weight to this weight. Then, as I said before, using exponential synapses, and we specify their 1 parameter tau, this is a time constant, to our time constant. And then finally, we set up the sparse connectivity. So we use this fixed number pre with replacement rule, which basically means that for each postsynaptic neuron, you sample the call length number of presynaptic partners with replacement. And all these connectivity initialization things are done on the GPU. So this really speeds up building large models. Again, we build our model, and we go on to the simulation. So Again, here we're looping 3 or 4 training images. The only difference is, as well as resetting our projection neurons, we're also resetting our GeNN cells. And because the exponential synapses have also got states, they've got dynamics with this tau. We're also resetting what we call the INSYN. This is like the output current from the synapses for the PN to KC connection. And for this, we just zero it and we upload it to the device. So now if we run this, so you can see we're getting some activations from the GeNN cells, but as Thomas was saying before, this is not a very stable sparse code. We're getting between 950 GeNN cells. So it's very hard to learn. It's very hard to learn It's very hard to learn from this. We want much more even numbers of GeNN cell activations. So to do this, we look to the biology that Thomas was talking about before, which is this giant inhibitory neuron that we see in the insects. So let's start the model actually. So the model, what we want here is basically when a fixed number of GeNN cells is fired, we want this giant inhibitory neuron to fire and then inhibit all of the GeNN cells. So for this, we want to you could do this with a more complex model, but the simplest way to do this and not have to sweep the parameters forever is to use a really simple integrate and define model. So all this does is this neuron's got one parameter, which is its threshold, and it's got one state variable, which is its voltage. The SIM code is the code that's run every time step, and all this does is add the incoming synaptic current to the voltage. And then it's got a threshold test, so if the voltage crosses this V threshold parameter, it emits a spike, and then it resets the voltage to 0. So it's a very simple neuron model, and as such, the only high parameter we configure is this V threshold, which is 200. So this, in an ideal world, this would mean that you'd get 200 GeNN cell spikes, inhibition would fire, and that would be it. So your codes would all be 200 out of 20,000 codes. So we want to add this to the model. So true to the insect is a single one of these neurons using this integrate and define model we defined. There's a quick thing: when models are specified as strings, it means they're kind of ones built into Gen, and these ones that are actual Python objects are ones we've defined in Python. We don't bother recording it. All it's going to do is emit one spike. It's not particularly interesting. But we now need to define this recurrent connectivity with the GeNN cells. So going from the GeNN cells to the giant inhibitory neuron, we have dense connectivity because all the GeNN cells are connected. And again, we've got a fixed weight, in this case of 1, because we really want to use that 200 threshold as a spike count. And we're using this even simpler synapse model. So this is a delta synapse, so basically all of the incoming current is dumped into the neuron in one time step. So again, we really just want to use this as a spike counter. So that's how we're configuring it. However, going the other way, we've got a slightly more complex model. So we're using, so this is going from the inhibitory neuron to the GeNN cells. So we've got a large inhibitory weight. Like, remember, our other weights are sort of order of 0 point something. This is a -5, so it's a very large negative weight. And again, we've got an exponential synapse. So the idea of this is that the exponential synapse will spread out the inhibition for a few time steps, so it will really kill off the GeNN cell activity. We built our model again. So here, this is again very similar. So all we've done is we're now resetting the GeNN neuron, and we're resetting its exponential synapse. We don't reset the GeNN cell to the GeNN synapse because that is a delta synapse with no state. So here you can see a much better picture. You can see that we're getting much more even numbers of GeNN cell activations. We're getting somewhere between 250 and 300, which is fine. It's very hard to get it that much close to 200. And you can really see in these raster plots where the inhibition is kicking in and killing off all subsequent spikes. So this is hopefully a code that we can actually learn. So we can now go on to the final layer of this model, where we're going to add in the learning. Right, so we've got a few more parameters here. I'll talk about them after I talked about the model. So the key thing here is that we've defined a new STDP rule. So this is a very simple symmetric STDP rule. So basically it's a double exponential curve, the kind of thing you often see in inhibitory STDP rules, in fact. And you've got, when the spikes are at the same time, you get potentiation, and then with this exponential fall off, you get less and less potentiation until a point where you actually get depression. So if the spikes are too far apart, then you get the too far apart, you get depression. So what we're going to do is we're going to stimulate what we call the mushroom body output neurons. So the correct class we stimulate with sort of constant input throughout the trial, and this SDP is basically just going to do your dumbest possible Hebbian learning. So this SDP has got a few parameters. It's got a tau parameter which defines the width of the window. It's got this rho which defines the like how much depression you get for spikes that are outside of the window. Eta, which defines the learning rate, and W min and W max, which the range of weights. So it's a simple additive rule. We just clamp the weights between these two values. So we previously set up the parameters for this SDP rule. So we have a time constant at 15 milliseconds, and we've got some values for the rho and eta that we found through a parameter sweep. And finally, we've got this current that we're applying to the mushroom body output neurons to generate constant spiking throughout the time steps. So we now finished building our model. So we add the mushroom body output neurons. We've got one mushroom body output neuron for each class. So with MNIST, that means there's 10. We add a second current source to the mushroom body output neurons, so we can drive them with this training signal. And then finally, we add this plastic connection between the GeNN cells and the mushroom bodies. And here you can see we're using dense connectivity again, but we're using this individual G, which means there is a state variable for each synapse, which you obviously need here because you're learning individual weights. And we start the weights at 0, and we use the symmetric SDP rule. Again, we build our model. So again, this looks very similar, apart from the fact that we're also applying a current to the correct training label. We're applying a current to the mushroom body neuron, corresponding to the correct training label, and we also upload this to the device. We've also got yet more state to reset, so we reset the mushroom body output neuron state, and we also want to reset these spike times. So because the SDP rule is event-based, you basically want all the spikes that happened in the previous. You want it to ignore the spikes that happened in the previous endless digit. So what we do is we just reset the spike times back to very large negative floating point numbers, so that the exponential decay from them is 0. And now this will sit here and train for some time, and I'll go on to the next slide because this is not a good way to spend your time. My laptop is not the ideal machine for training models. So I'll leave that training in the background, and as I said on Blue Peter, here's what I made earlier. We can load some pre-saved weights. This model is basically exactly the same as the other one. You've just removed the STDP. So in this case, we've got the GeNN cells to mushroom body connections are now static, and we're loading the weights that we learnt earlier using these from the NumPy file that we saved at the end of our script. So first of all, we just run the first 4 examples, so you can see what the model does. So here you see you've got your GeNN cell activations, and now you've got these mushroom body output neuron activations as well. And we're actually plotting 2 horizontal lines here, a dotted red line for the classification the model makes, which we treat as the first spike, and a green line for the correct classification. And in this case, they're all correct, which bodes well for our model. So they're all on top of each other. So I think that suggests the model's working nicely. So we now run this on our data set. And stop the training. This might be too much for my laptop to handle simultaneously. So, there we go. So this is clearly not a cutting-edge endless classifier, but I hope it's a more meaningful example of how you might build a non-trivial model in Gen than sort of just building a bounce around network or something. Once this finishes, unless someone's broken in a hilarious way, You should get a performance of about 75%, which is clearly not amazing by modern standards. But it is learning in one epoch using STP, which is as we've spent the last quite a lot of the last week fiddling with this model, is even in 2021 not entirely trivial. And in fact, the performance can be improved quite a lot by reducing the simulation time step. So if you drop it to a smaller fraction of a millisecond, you get quite a lot better performance. And this is because that code that we were seeing before, you can see in this case quite a few of the output spikes are quite close in time, and there's only 20 milliseconds to space them out in. So if you drop the time step, then you get better classifications of kind of close, and here we go, yeah. So we got 75% on our test set, and that is the end of my interactive part of this. I'll stop screen sharing. If anyone's got any questions, we've got a few minutes. How do I stop sharing the screen?
I can do it for you.
Oh, thank you. I think that's probably a good idea. Yes, if anyone's got any questions, Thomas would be happy to answer.
Looks like everyone is happy. Or is
We do have a question.
Oh, good. Right, so it's very simple in this case. The correct digit is purely the one that spikes the first. So we view the mushroom body output neuron that spikes the first as the correct output because our input is event driven, so it's very sparse spike-based code with earlier spikes for more significant figures. Then the output is also time-based. If that helps.
And if you wanted a more realistic, like insect brain inspired thing, you would probably put lateral inhibition on those output neurons, and there would only one neuron be spiking, the first one, and the others would be inhibited, right? And then it's very clear that's the output, right?
Okay, thank you.
You're welcome. So by the way, if you do the smaller time steps and things, you get about 90% performance or 10% error, which isn't great, but this is really the most dumb model in a sense for MNIST you could do. And given how dumb it is, I think 90% is actually not that bad. Okay. Yeah, so I hope that it gave a bit of an impression how GeNN works and how you can use it. If you have a bit more time and you're interested, have a look later. We're happy to answer questions offline at a later time as well, obviously.
Yes, I can add that asynchronous discussions can be done via our Discord server all the time during and after the conference. So don't be shy, anyone. Just ask and everybody can have a nice chat. We do have text and chat channels, so you can meet and talk live if you want on Discord. Since we don't have any more questions, I am gonna invite our next speakers. We are right on time. Thank you very much, Dr. Novotny and Dr. Knight.
Thank you.
Thank you, Anka.
People. Gosh, I don't see.
Hi. So actually, Dan Goodman won't be here today.
Okay, I was just I was just looking for him to invite him on the screen. That's fine. That's totally fine. So let's just get started. It is my pleasure to invite on the screen Dr. Marcel Steenberg, who is going to talk about Brine 2 simulator. Go ahead.
Okay, started the screen sharing. I hope it's coming up.
It's coming. I see it. Everything
Okay, great. Okay, yeah, thank you, everyone. Very happy to be here today and talk about the Brine 2 simulator. Maybe first I start with a little bit of history about where the Brine simulator is coming from. So originally it was created by Dan Goodman and Romain Bretman. Both of them were at the ENS in Paris. Now Dan Goodman is at Imperial College London, and Romain Bret is the group leader of the group I'm in at the Institut de la Vision in Paris. So the work started already in 2007, so it's been a while ago. And it's a simulator that is used both for research, but also a lot for teaching. And maybe one of the phrases that kind of summarizes what the intention behind Brine is that it's a simulator should not only to save the time of processors, but also the time of scientists. Because in their own work, Dan and Romain observed that quite often the way, the speed at which they progress in modeling is not so much limited by the simulation speed of the simulator, but more by how long it takes to get the model from the idea to a running model. So the idea with Brine is to make it very easy, straightforward to get from a model idea basically to a working and running model. So also in contrast to quite a few other simulators, it doesn't come with a library of built-in neural models, the adaptive exponential integrate and fire model with exponentially based synapses or something like that. But instead, it gives you the means to describe basically any model that you can think of in mathematical language, and I'll talk about this in a bit. So I became involved mostly around 2014, where we did a big rewrite of Brine to create Brine 2, which was built around the concept of code generation and other improvements, but I'm going to explain what code generation is. And of course, it's free and open source, so we are very happy about contributions, and you can see all the code and all the discussions online on GitHub. So let me explain a bit how the idea behind Brine. So Brine's philosophy is that it should be really straightforward to go from a model description in the typical language that we share our models in papers. In the method section, you see a bunch of equations, differential equations for, say, how the membrane potential, ion channels, etc. involve, and what happens for spike events, maybe some discontinuities triggered by spikes. And this can be translated into Brine syntax, which also uses these mathematical language. So equations. Basically, in Brine, you write equations in as close as possible we can get to mathematical language by just writing text. And something that it also sets apart from quite a few other simulators is that it has built-in support for physical units. So not only within the equations, the consistency of units is checked, but whenever you put things into your model or take things out of your model, they have physical units attached, so you cannot make mistakes, and it makes, after a bit of getting used to it, it makes for a very intuitive and convenient use of model data. And finally, it's written in Python, so it's not just a Python backend to something, a Python front end to something. So we try to make really good use of Python, give useful error messages, and so on. So about the, and of course, not to forget, we have quite extensive documentation, hopefully friendly community, and we encourage contributions, etc. So let's talk a bit about the technology behind it, because all this flexibility, you can write whatever model you want. Of course, you could think it comes at a cost, because we cannot have pre-optimized handwritten models for you. So the way Brine solves this, a bit similar to the GeNN simulator actually, is the concept of code generation. So you write your equations, in this case, basically the simplest differential equation you can think of. And as a first step, Brine does the numerical integration of these differential equations. So we provide a bunch of numerical techniques like Wunsch-Kutta methods or the exponential Euler method. But in this case, if the equation is that simple, we can actually analytically exactly solve this equation. So this is what is done here. To advance one time step to the other, we just integrate the differential equation. So that's the first step. The next step is to convert this into a target language code. So the main target language we support is C++. So it does a bit of translation and a bit of optimization. In particular, it pulls out things that don't have to calculate it for each individual neuron if there's a group of them, but things that can be calculated once for a whole group of neurons if they share, for example, in this case, the time constant. So if we have a homogeneous group of neurons, we don't have to do this exponential decay once for every neuron. We can do it once and just multiply it with the membrane potential of each individual neuron. And so this is already a C++ code. And then for each kind of task that has to be done during a simulation, there's a little template. Here in this case, the template basically just means loop over all the neurons. And there's a bit more fancy stuff, so we can do this also with multiple threads, for example, for a more optimized performance. But that's the basic approach that we use for everything. And then there are two different modes of executing the code. So we have given them the names runtime mode and standalone mode. So the runtime mode works in the way that these blocks of code that I was just talking about, they are compiled, and they are little bits of code that do individual things, like advance the state variables of a group of neurons about one time step. But the main control over what happens during a simulation is still in Python. So there's a loop in Python that loops over all the time step. And within each time step, it calls out to all these little individual compiled code bits. This has an advantage that we're super flexible. So we can completely interact between the Python and the compiled code. So we could, I don't know, plot data after every time step, or we could intervene. We could do whatever we want by just writing a Python function and telling Brine to call this function every time step or every other time step or whatever we want. But it comes at a cost, because we have quite a bit of overhead from running this loop, going into the compiled code bits, getting data out of them, and so on. So it's not the most performant way of running Brine. The most performant way of running Brine is the so-called standalone mode. There you basically, you write your model in exactly the same way as you do now, usually, but then you switch on the so-called standalone mode. And what this does is that instead of having a Python loop running your simulation going over time step, it takes everything of your model and puts it into a completely standalone C++ code. So that means we also generate the C++ code to initialize variables, to run a simulation loop over time steps, maybe then change a variable and run another loop. All this stuff will be put together in a completely independent C++ directory, basically. So you could take this and go away and forget about Brine and just run your pure C++ code. But of course, we're also integrated into Brine. So from running your model, you actually don't notice what happens under the hood. But the difference is that when you run it, when you say, okay, simulate my model for a couple of seconds, that actually hands over control completely to the C++ code and only gets the results back from the C++ code. So the big advantage, of course, of this is it's fast. Another advantage is we can use this technology to tailor our code generation mechanism to other platforms. We are not limited to generating C++ code this way, but it could be basically whatever. But of course, it comes at a cost. The disadvantage is we're less flexible now. We cannot run arbitrary Python code at the end of every time step, for example, because we are handed over control completely to the C++ code. Okay, hopefully this gives you the general idea of what the difference between these two modes is. Now, what is the domain of Brine? So what can you use it for? Maybe just quickly, the kinds of model you can simulate. So you can simulate, of course, all kind of integrate and fire models and all the variants of it, adaptive, exponential, integrate and fire model or whatnot. You can also integrate all kind of more complex single compartment models. So these kind of Hodgkin-Huxley type models where you have several nonlinear channel dynamics, multiple differential equations for not only your membrane potential, but also for gating variables and so on. This is kind of like the core domain of Brine. We do also have support for multi-compartmental modeling, so more complex model where you really model the spatial extent of a neuron. So you have dendrites, you have an axon, you have a soma. The membrane potential can propagate from the dendrite to the soma and so on. You can do this in Brine. The support is still a bit limited, and especially for complex morphologies, it's not super convenient to use. So at the moment, I'd rather recommend using this for more like kind of artificial morphologies, ball and stick models, and so on. If you know these kind of ones. And for the kind of size of the models, Brine is really a simulator that is targeted at models that can be run on a single machine, so your laptop, your workstation, whatever. It is not at all meant to be run on supercomputers, so it doesn't do multi-process communication. It cannot send information from one computer to the other to simulate really, really huge networks with billions of neurons. So if that's what you want to do, then Brine isn't a simulator of choice. On the other hand, we took some care that it runs on Linux, OS X, and Windows, so on all major operating systems. You should be covered. Just a quick, because people love benchmarks for simulators. As I mentioned in the very beginning, Brine wasn't meant to be fast as the first priority. It's meant to be fast to be able to write down models, simulate models, and express what you want to do. And speed only comes as a second priority. But of course, we spent quite a bit of time also to simulate the speed, because at some point, it can really prevent you from running certain types of models. So the green lines here are several different variants of the Brine simulator, and it's compared to a few other simulators. But the point I'm trying to make with this figure is not so much that we are faster than other simulators, because this very much depends on the model. And as I said before, as soon as your model gets too big to be run on a single computer, well, we can't compete in the first place because Brine doesn't run on multiple processors. But what I want to show here is this is twice kind of the same model, a sparsely connected leaky integrated fire neuron model. But the difference between the two models is that one case, all the neurons have the same time constants and a few other parameters. And in the other case, it's completely heterogeneous. And you see in this example here for a few of the simulators that doesn't make a difference at all, because they come with a built-in model for these leaky integrated fire model with exponential current-based synapses. And well, so it doesn't really make a difference whether the population is heterogeneous or homogeneous. It always runs the same code. But it will do redundant calculations in the homogeneous population case. And for Brine, it's different because we generate the code. The code will be quite different if the whole population is homogeneous, because this is reflected in the equations, and Brine knows about us, and it does these optimizations that it pulls out the common terms out of the loop, basically, so it will only calculate them once and not once for each neuron. And that's just why you see these green lines are quite low here for the homogeneous population, because they are basically not running the same code in a way, these different simulators in this case. Okay, now let me just show you a few examples of what you can do with Brine. Not real life examples, but more like toy examples, but show you some of the specific features and strength, say, of the Brine simulator. So here's just for neuron models. You have basically all the freedom you like. So here, for example, this is an integrated fire model, which is a bit untypical because its threshold is not a fixed threshold, but it is adapting. So with each spike, it increases a bit and then relaxes a bit back to a certain value. And in addition, the threshold is noisy. So it has a kind of noise process built in that in Brine you can access with this special variable that is predefined for you, xi. So in this case, instead of just having a single differential equation for your membrane potential, here you have two differential equations, one for your membrane potential and another one for your threshold, and you write it down. And in your threshold condition, you refer to this varying threshold. So, and you could change the threshold in whatever ways you want, remove the noise, make the adaptation different. Here, this it's an adaptive adaptation, but it could be multiplicative, whatever you can think of. You don't have to wait for someone else to add this model to the simulator. You can just change the equations yourself. This flexibility is not only restricted to neurons, but you have the same flexibility for your Synapse model. So if you want to have something like, for example, short-term synaptic plasticity or STDP or some kind of fancy variant of STDP, again, if you can express it with equations, you write these equations down in this Brine syntax, and your model gets simulated. So I'll speed a bit up. We're not going into too much detail for each of these models to not run too much over time. This flexibility, it not only extends to the definition of neural models and synapse model, but also to the definition of the way synapses or neurons are connected with synapses, for example. So one very powerful feature for this is that in addition to the model equation, a model can contain arbitrary attributes. So you can give each neuron a position in space, for example, or some other arbitrary labels. So here, in this case, a neuron type. And as soon as you have this and then define them in some way, so here we just randomly assign neurons to one of two types, and we give them a position, like a regular position arranged on a grid. And as soon as you have this, you can connect them with these kind of descriptive connection strings. You could say, here what we say is we only want to connect neurons if the pre and the post-synaptic neuron have the same type, so only connect neurons of the same type. And then there's a probability that is given as a function of the distance between the two neurons. So there's a strict rule, only connect neurons of the same times, and the probabilistic, the closer together the neurons are, the more likely they are connected. And this gives you connection patterns like shown here on the right. And finally, a last example, these equations, nothing restricts you to using them only for the neuron, the synapse model. You can also use them, for example, to have parametric functional versions of your stimulus. So for example, here we have an injected current that is part of the neuron equation, so it gets injected into the membrane potential. But in addition, it is given as a function of time. So in this case, it's a sinusoidal infuse current with a certain amplitude and a certain frequency. And in addition, we have these code that is, well, as the name says, run regularly. So here there's a bit of code that is run every 50 milliseconds. And this chooses randomly a new amplitude and a new frequency. And this is then taking account in the current here. And in this case here, it's different for all three neurons. So they get a different input current, and they, as a consequence, they spike differently. Okay, these were the examples I wanted to show. And now a few things that are around Brine. There are a few extensions, kind of, because as I mentioned before, we made this backend, especially the standalone mode. We designed it with extensibility in mind, so you can replace the backend by something else. And there's kind of 1.5, one in progress backends for this. So there's Brine to GeNN, which links to the GeNN simulator that you just heard about in the previous showcase. And there's a Brine to Cuda, which is currently in progress, but hopefully released soon, which directly will generate CUDA code from a model. And then there are two additional packages called Brine to Tools and Brine to Model Fitting. And let me just give you very quickly an idea of what these do. So Brine to GeNN, as the name suggests, is a link to the GeNN simulator that you heard about that makes use of the GPU. So again, an idea to make your simulations faster. And the way we designed it we made it very simple to use this this extension. So you describe your Brine model in the usual way, and then you just add these 2 lines, import Brine to Gen and set device Gen to your code. And instead of generating the usual C++ code, we'll switch and generate Gen code behind the scenes, which then again behind the scenes will generate code for the GPU in Cuda. Then everything will get compiled and so on and run. And the user ideally won't really notice that much, except that they have to wait a bit until the simulation actually starts. And then it runs as if it were a normal Brine simulation. And then very, very much in the same spirit, that there will be soon a Brine to Cuda package, or it already exists, but it hasn't been released yet, which would mean adding these 2 lines to directly generate Cuda code instead going via Gen, which would have the advantage that it would support more of Brine features, because Brine sometimes there isn't an exact translation from something that Brine does to Gen, and then we cannot really support this feature, or the other way around. We cannot, not for every Gen feature there's an equivalent in Brine, and that in this interface directly made for Brine to Cuda, that wouldn't be a problem. On the other hand, of course, this interface won't benefit from all the work that Thomas, Jamie, and others put into the Gen simulator. So Gen simulator is very optimized. It has been around for a long time, but we'll see. I'm quite excited and happy to see it out yet soon. And very quickly about 2 other packages. So there's Brine to Tools, which, as the name suggests, is kind of like a general tool collection. So for example, it has a few tools for visualization, which are really meant to be used very simply, especially also for things like interactive exploration of your models or interactively coding your models, for example, in a Jupyter notebook. Provides this nice Brine plot command where you can just throw in a recording device, so something that records a state variable during your simulation, and it does a reasonable plot where it labels things with names and units, and it knows about what is recorded and so on. Similar thing for, you can just throw in synapses and it will plot you some representation of the connectivity structure, either something that actually shows you every connection, or like in this example, where there are here like 4,000 times 4,000 or 4,000 times 3,200 possible connections, where it doesn't make sense to really plot each of them. It does a kind of like a density plot of the connections. So this can be quite useful. And then there's also support for an import-export framework that is the result of a few generations of Google Summer of Code students. So we have some support for exporting and importing models from into a NeuroML, and also a quite recent addition, which also hasn't been released yet, of exporting nice text-based descriptions of a model. So you write your model in Brine, and then in addition to getting the results, you can also make a nice text-based description that you can potentially then include in a paper, for example. And finally, there's a tool called Brine to Model Fitting that you can use to fit models to experimental data. So you describe your model, again, using Brine syntax, and then you plug in some experimental data that you have measured, or some fake experimental data that you simulated yourself. And then we've wrapped a number of packages that provide optimization methods, and we provide you with a number of error metrics that you can use in these, or you can write your own, and then magically it fits your model to the data. And there's some ongoing work with this year's Google Summer of Code student also wrapping around a technique called simulation-based inference, or more specifically a package called SPI, developed by the Maker Lab, which is instead of having a single best fit to your model, it instead trains a network that basically learns the association between parameters and some features you're interested in, and then allows you to basically estimate a full posterior distribution of your parameters, which is obviously a nice thing. If you're more interested in this, please come to poster 131 on Monday, 9 p.m. my time. Well, look it up. Poster P131.
Very nice.
Okay, that's
Dr.
almost it. Very final remark. If you happen to already use Brine, or if you might use it, or if there's something preventing you from using it, please fill out our survey that we just put online. So you go to tinyurl.com/brine-survey-2021. We would be very thankful for some feedback of what we should improve in the future. Okay, and with this, there's just a bit of information where you can get more information, the website, documentation. We have a support forum, GitHub for the code, and of course a Twitter account and a few papers that we wrote about Brine. Also, don't hesitate to ping me in the Discord chat, or of course come to the poster on Monday evening. And finally, you find a link to the slides I just presented also on the CNS schedule instance, so you can. You don't have to write down the links now. Just click on them in the presentation.
Thank you, Dr. Steenberg.
Thank you very much, and I'm happy to answer questions. I'm actually seeing one. Interested in being able to run Brine in the browser so we can push. Okay, yes, indeed. Yeah, running Brine in the browser, we'd be very interested in that as well. That's actually also a point in our survey, so please go to the survey and vote for it if you're interested in it. And there was also a bit discussion about around this topic on our discussion forum recently. So please join this discussion. Yeah, I'd be very happy to work on this, or even happier to have someone work on this.
Did you post a link on in the chat? For the feedback?
To the slides or to the forum, or to
the feedback thing you said?
Sorry, no, I didn't, but I probably should.
Yes.
Let me just type it out, which is a bit weird, but it should be this one. Oh no, I should make it a link so you can actually click it. Let me try this again. Up. So this, I hope I didn't misspell it. Yeah, no, that's correct. Okay. Are there any other questions? I didn't really follow the chat, so in case there are questions in the chat, I didn't. What is? Oh yeah, Thomas posted that GeNN works very well. Indeed, it does. Okay. If there are no more questions, I guess I'll hand over to the next speaker, right?
Right. Thank you so much, Dr. Steenberg. The discussion is not over. It can be done on our Discord server. That could be during the conference or afterwards. So we do have a Discord server.
Stop my screen sharing, and
that's fine. That's fine.
Should I just stop my video? But that
no, I'm doing all the work here. No problem.
That would
Thank
leave
you very
a black
much.
screen for everyone.
Bye. All right. So a minute of delay. I'm inviting on the screen.
Hello.
Our next speaker, Dr. Ankur Singha.
Hi, Ankur. Hello.
Hi, Ankur. Yeah, it is my pleasure to have Dr. Ankur Singha talking about CompNeuroFedora. And with this short one, we are right on time. So just go straight into the talk, please.
Great, thank you. I'll just share my screen and then we can get started. Okay, so hopefully everybody can see my screen and everybody can hear me nice and clear.
Nice and clear, all good to go.
Great. Okay, so we've already seen two excellent talks about tools that are critical for us as computational neuroscientists. And in this talk, I'm going to try and make it a little bit easier for you to use these tools. So I'm going to speak about Neurofedora. And as you see, our goal or our credo is to have free software for free neuroscience. I always like to begin by a quick reminder of what our ideals are. So it's not enough to do excellent research. It's not enough to publish your papers in high impact journals and all that. It is important that all of this is done in the right way so that everyone has the freedom to study, modify, and share the scientific material that we produce. And I find sometimes when I get really bogged down with work that the priorities become to make sure that all of this material is available to other scientific users. So this could be scientists, academics, students, and researchers. And sometimes I tend to forget that everyone is not limited to the scientific audience. Everyone means everybody, irrespective of whether they work at universities, irrespective of whether they are in developed countries where they have access to infrastructure. So everyone should mean everyone in the true sense of the word. And so that is the ideal that we look up to. That is the ideal that we should try to reach. And the open science movement, luckily, is gaining a lot of traction. There's a lot of discussion about publishing, for example, open access. Their code, but also their data, all the post-processing scripts, all the graphs that they generated. So we are going in the right direction. But yes, there is still some work to be done on that front. Now, the idea of open science is not new. It stems slightly from the free and open source software movement, which is quite old now, started a long time ago at MIT. And the idea of the free and open source software movement is that users should have the freedom to study, modify, and share software. And now you see how this is very, very similar. In fact, it's parallel to the open science requirements. And I know the common jargon here is open source software. A lot of people know what OS means. A lot of people will talk about how their tools are open source. But the truth here is that we focus on the user, and the user should be free. And that is why some of us prefer to call it the free and open source software, because the word free here is very, very important. And the free and open source software ecosystem is very, very huge now. Almost everybody now has used or does use Python on a daily basis, which is an important part of the free and open source software ecosystem. All your other languages, Julia, Scala, all of these are open source. R is open source. And the idea is that you have access to them. You don't need to pay, unlike your Microsoft products or unlike your very expensive MATLAB license. All of these things, as long as you have access to the internet, pretty much, you will be able to use these tools. And you will be able to, at the same time, you will be able to study them. And you have the capability of modifying them if you really wish to. Right? So open science goes hand in hand with the free and open source software movement. In fact, I don't think it would be wrong of me to say that the open science movement cannot exist without free and open source software. Right? All the infrastructure, all the software we rely on is open source. Now, a lot of people would have either heard or used Linux distributions. They are, I would say, the prime sort of candidates of the open source software and free software ecosystem. These are the more common ones, but as you see there are actually thousands more. And this comes from the fact that all of the source code is free, which means small sets of people get together. They have a common interest. They want to do something in a particular way, and they can start their own distribution. When these communities get large enough, for example, Debian is a very large community, Ubuntu is a large community, some people use SUSE or Arch Linux, they're all large communities, but they all started from this core idea of the source code is there. I'd like to do something in a certain way. I'd like to follow certain software practices, and like-minded people can come together and then develop their own operating systems, right? So there are pretty much no restriction on what you can do with the source code. For those that haven't tried any of these out, you can go on to the links I have here, or if you look for DistroWatch, it's a website dedicated to Linux distributions. You can find reviews, you can find download links, and so on. And now you'll notice that one of these operating systems I've listed here is called Fedora. And as Neurofedora would give it away, this whole project is part of the Fedora open source, free and open source community. It's a Linux community project. It is sponsored by Red Hat, who are a very big player when it comes to enterprise Linux solutions. And the community promotes free and open source software by producing the Fedora Linux operating system, right? So the way you have Windows and Mac, you also have the Fedora Linux operating system. It is very similar to Ubuntu, but the underlying technology is slightly different. And the idea is that it's not enough to just have an operating system. People have to be able to do things with it. People have to be able to work on it. And that's why in a short snippet, the goal of the community is to make an operating system and to make it easy for users to use it for whatever purpose they want. So it doesn't have to be science. It doesn't have to be something technical. It doesn't have to be software development. I know a lot of people that use it for design work, artwork. I know a lot of people that use it for music production. As I'll show you later, we have people that use it for astronomy research. There are people who are using it for big data. The point is that you have this platform, and we can make it easy for people to use this platform for their particular use case. And what is good about the Fedora Linux community project is that it's part of the RPM ecosystem, which also includes Red Hat Enterprise Linux, which I had mentioned before, but it also includes CentOS and Scientific Linux. If you have used a supercomputer, for example, at your university, it's most likely running either CentOS or Scientific Linux, or it's running some variation of these, because these are quite standard now for supercomputing systems. So the advantage here is that all the work we do for Fedora can very easily be translated down to all of these systems that run on supercomputing platforms. Okay, they all basically form part of the same pipeline. To give you a little idea of how vast the Fedora Linux community is, this is now a slightly out-of-date community organization chart. And if you can see my mouse, you can see that there's a council in the middle, which makes executive decisions. But at the same time, you can see all of these arms going away from the council. So you have people that focus on different programming language over here. So you have everything from PHP to Erlang, which I haven't ever used in my life. But you also have people that work on software security, right? So there are people who will look at, for example, security issues in software and report these and submit patches for them. You have people that work on computing architectures. Most of us use Intel-based 64-bit computing platforms. Some of us will have older machines that are still 32-bit. But apart from that, there are specialized platforms like the Spark and PowerPC. And Fedora supports all of these, because the way the community works is a bunch of people come together, they want to work on something, and they'll share infrastructure that the community has, and they'll just work on whatever they wish, right? You don't really have to take permission from anyone. As long as you follow the code of conduct that the community has set out, you're welcome to go in whatever direction you wish. And you can see here that because we are fiercely pro-free and open source software, we are also fiercely pro-diversity. So there are special interest groups that work on diversity and outreach. On the right-hand side, you can see we have classroom sessions where we sometimes take short sessions to teach people computing technologies, like, for example, Git or Bash, things similar to what the Software Working Group has done at CNS this year. You also see that there are people that like to work on artwork and design. And in this huge chart, a really small part forms the neuroscience special interest group that I'm talking to you about today. So it's vast. We all share infrastructure. Whatever one special interest group will contribute will be advantageous to the rest of the community. It's structured that way. And anybody can come in, and as long as they agree to follow the code of conduct, they can start whatever project they wish. So you've got astronomy folks, you've got amateur radio folks, the folks that work on robotics, 3D printing, and so on and so forth. Right? There are no limits on this front. So while Fedora wants to develop a Linux operating system and make it easy for users to do stuff with it in order to promote free and open source software, the neuroscience special interest group within the community focuses on this particular domain. So we want to make it easy for you to do neuroscience on Fedora Linux platforms. And the way we do this is we try and make it as easy as possible for you to use neuroscience tools on Fedora Linux platforms. The simplest way here is that you download Fedora Linux from getfedora.org. There are multiple variants. So, for example, we produce an operating system that works well on workstations and laptops. But if you want to deploy a server, there's a different version with a different set of software for servers where you won't have a graphical interface, but you will have an administrative interface in a web browser, for example. It's called Cockpit. So you can install any of these. You can install it on your hardware. You don't have to, because as I'll show you in a minute, you can run these installer images live without installing them. And the way you have Brew for Mac and apt-get for Ubuntu, for Fedora-based systems, you have the default package manager called DNF. So install a Fedora Linux operating system, use the package manager to install whatever tools you need, and that's really all. You can just proceed with work. So that is the simplest, most general way of going about it. But because I work in computational science and I tend to be slightly lazy, I went ahead and worked with the other folks. And what we did was we've taken the Fedora Linux operating system and we've packed it with lots of common tools for computational neuroscience. And so now you have an operating system that we call CompNeuro that already comes with all of this software pre-installed. So you don't even have to install a general Fedora Linux operating system and install your packages. They're already there for you. There's quite a huge list of tools. I'll name some of them here. Arbor, you've just heard about Brine. There was a tutorial on Arbor, I think, earlier today. There's Nest, there's Neuron, there's also NetPine, which had a tutorial earlier today. There's Steps, there's the whole NeuroML ecosystem that we include there. There's a full Python stack, SciPy, NumPy, Matplotlib, IPython, which includes Jupyter Notebooks, SymPy, Pandas, other tools like Plotly, Bokeh. These are all new plotting libraries that have become increasingly popular. So we pack all of this in this installer for you to use. I like to give a special mention to GNU Octave because the way the MATLAB ecosystem works is it's such a strong ecosystem that it takes quite a bit of effort to move away from MATLAB. But for the first step, what you can do is you can use GNU Octave because while it's not meant to be a drop-in replacement, it's meant to be feature compatible. And in most cases, at least whatever MATLAB scripts I've experimented with, you can use them as they are in GNU Octave. Now, the difference is that for MATLAB, you generally need to work at a university because individual licenses are quite expensive, whereas GNU Octave is free and open source software, which means you go to the website and you download it. Or you use Neurofedora, and it comes in the installer for you. So I can show you a quick demo now. For this, I'll move to my virtual machine tool. Again, where people would use VirtualBox or VMware. On Fedora, we have a free and open source software-based virtualization solution. Very standard, so I just need to find my installer file that's here. And I'll just give it a little bit of more juice to make sure it doesn't lag too much. So we're running this from the ISO itself. I haven't installed it anywhere, right? All I've done is downloaded the ISO from the website. And I'll show you that while this loads. So this is our website. The link is on Sked. It's called the CompNeuro Lab. And there's a big download link over here that nobody will miss. And we show a few featured applications that are quite well known. But this 9 out of about 200 software tools that we include. So all you really have to do is click on download, and then it gives you a bit of information about how to do it, how to go about it. And once you click on this link, it'll download the installer image for you. They're also supporting resources. I'll drop links about these. They're all on Sked, but I'll show you links for them later. And in general, we are one particular variant of the Fedora Linux operating system. As you can see here, there are other variants for people that want to do astronomy, people that are interested in design. There's a whole installer full of free and open source games that work great on Linux. For Python lovers and people that teach Python, there's a Python classroom. Musicians, people interested in security, robotics, and there's a general scientific computing variant, which comes packed with general tools, not so much neuroscience focused. So you can just go to this website, click on CompNeuro, and you come to our page. Meanwhile, the virtual machine has loaded. So this is a completely brand new installation. Well, it's not even an installation. I'm running it live from the image. So it's not been modified in any way. If you click on the right on install to hard drive, the installer comes up, and you can choose how you want to install it. I'm just going to show you this now. So this is the GNOME desktop environment. As you can see, the days where people looked at Linux and said, well, it's clunky looking and it's not polished, those days are far gone. It looks nice and sleek. All of this is now touchscreen activated. So if you have a laptop that has a touchscreen, you can use the touchscreen to navigate all of these. You've got your app drawer, as you would. You've got all of these tools included. So for example, you can see Gnu Octave here. We always throw in Vim and Emacs just because a lot of us use them. You've got your whole Office suite, which is not Microsoft-based, which means you don't have to pay to use. Of course, you'll have your browser. Firefox is our choice of browser because it is the free and open source software browser of choice. You've got your file browser and everything else. So it's a standard operating system. And when it becomes really fun now is that in my terminal, I can run Python, and I can import all of this. What else can I think of? Neuron, I think we also have Netpine. Right, so all you've done is downloaded the installer. You haven't even installed it, but all of this software is already at your fingertips. You can just start working immediately. You don't have to worry about figuring out how to install them. You don't even have to worry about setting up a virtual environment. Right? If you want to, of course, you can set up a virtual environment because Python is installed on the system completely. It's also got Jupyter notebooks installed, which are becoming more and more common, as you would have seen at all our tutorials today. Right? So in a sense, it's an operating system with all of this pre-installed. And it's not only meant for scientific use. As I've showed you, it's got your Office suite, it's got your usual file manager, it's got your music players and so on. It's got your calendars, it's got an application for photos. You also have a graphical software installer. I won't show that to you now because it takes some time to update metadata. But in every sense, it is a standard operating system, which now has a lot of tools for computational neuroscience built in. Okay, so all you really have to do is go to the website and download it, and you'll have all of this ready to use on your system. For the time being, I'm going to turn this off. Okay, so that was the second use case where you now have an operating system full of software for you. And the way we package these software tools in the Fedora community, it also allows us to create container images for them. So the way you have the Fedora Linux installer for your workstation, for your laptop, you also have a Fedora-based container image. And what that means is that instead of installing a completely new system using the installer Linux ISO image, if you have Docker or Podman installed, all you really need to do is pull the Fedora image, right? You pull the Fedora container image, you can run it interactively using Docker or Podman, and then you can proceed to use it as you would a normal system. So with DNF, you can install Neuron, Brine, NetBine, steps, so on and so forth, and just use it interactively in that sandboxed environment. And those of you that are experienced with containers would also know that you can then create your own custom containers. So you can base them on the Fedora default image. You can install whatever software you need. And then you can actually package all your code into this container image. So for example, if you want to share your simulation code and data with somebody, yes, you can upload it to GitHub and they can clone it from there and then install it and so on. But if you really want to make it easy for someone, you can build yourself a container image and then just share the container image with them. All they really have to do is run it. They don't have to install anything. All your stuff is already in there. Think of it as an archive which can just run on your system if you have Docker or Podman installed. So not only do we give you the operating system, we also give you these containers that you can use. Containers are also very, very useful for testing and continuous integration. So if you do develop software or if you want to test out your model, you can really quickly pull a container image and just run it in there to make sure it works with a different version of a software, for example. So the different ways in which you can use this, all of this comes from the way we package these tools. And currently, we're about 30 volunteer contributors. Even though I am based at a research laboratory, the Fedora project is a volunteer community. So people don't get paid to work on it. We all work a couple of hours, maybe 3 or 4 at most every week to maintain these tools. And that much, when there are quite a few people, is quite enough to get quite a bit of work done. So at the moment, we have 200 software tools already there. Quite a few of them will be libraries that a user will never actually see, but they are well maintained nevertheless. And the importance here is that because we test everything out, we know that with a particular version of an underlying library, the software tool works really well, right? There's no doubt about it. And while we do have 200 tools in Neurofedora, there are another 200 in queue, because once you start looking into the neuroscience software ecosystem, you realize that there are so many tools there for different reasons. So Neurofedora also works as a good place to kind of integrate all of this in one place, right? So you don't have to go around looking. You can just go to our documentation and see what tools are out there. We have an issue tracker. We don't use GitHub because even though it is free to use, it is not free and open source. We have the Fedora community has its own Git forge called Paga. The source code for Paga is available, a bit like GitHub community, so you can deploy it yourself if you want. It's very, as you can see from the screenshot, it's very, very similar to GitHub. So we've got an issue tracker, but you can also push and pull Git repositories and have pull requests and so on. Finally, before we go towards the end, so there are different ways in which you can join the Neurofedora community. You don't really have to actually work on the software side of things. If you're just using the software, you're sharing the code, you're already part of the community. So please go ahead and do that. If you look at our list of tools and there's a tool that you use that it's not there, please let us know, because 30 of us use a certain number of tools, and then we rely on other people to tell us what else is useful for computational neuroscientists or data scientists or people that work in neuroimaging and calcium imaging and so on. And finally, help us include and maintain more software, because the more software we can integrate in one place, the easier it becomes for researchers to use. I said that wrong. The easier it becomes for everyone to use, not just researchers. And a special shout out to anybody that does develop software for neuroscience. Please get in touch with us and help us include it in Neurofedora. And while you're doing all of this, of course, the advantage is you learn about more tools. Because the Fedora community is a software development-based community, you get to learn a lot about software development, right? So we use Git on a daily basis. So all of us are very, very proficient in Git now because we rely on Git on a daily basis. You also learn a lot about building tools from source. You learn a lot about the best practices that are required in order to maintain these tools well. We interact a lot with developers. So if you look at some of the issues on GitHub, you'll see that a lot of them, well, not a lot of them, but quite a few of them will come from Neurofedora contributors who found a bug or an issue and have therefore contacted developers to try and fix them. And in general, if you do become part of Neurofedora and you communicate with the developers, you're helping them maintain all of the software that we depend on a daily basis. And the last slide for me is just how to get in touch. Luckily, you can just look for Neurofedora on your favorite search engine, and our documentation and blog should turn up because there's nothing else at the moment that's called Neurofedora. We have chat channels on Telegram. We also have them on Element. We also have them on IRC. You can also tweet at us. We have a mailing list, and we've got a form where you can suggest software. And with that, that is my last slide. I'll leave it up there. If there are any questions, we can do that.
We have 2 questions from Cengiz, and I'm going to invite him on the screen. It's easier.
Great.
We cannot hear you, Cengiz. You are still muted. Okay. We hear you now.
Do you guys hear me now?
Yeah.
Yes.
I wasn't sure if Ankur was done. I was just waiting.
No, I'm done. I'm done. Thanks.
I don't know. I wrote some questions. One question is kind of, I know like this is, you already guys selected Neurofedora and you've done all of this work, but why not something more popular like Ubuntu? Because there are so many more people using Ubuntu, and Fedora and Red Hat, the RPM stuff is not usually up to date and usually requires more work to maintain. But yeah.
Well, the first reason is this is a bit personal because when I distro hopped, I settled for Fedora. This was 12 years ago as an undergrad student. So I've been around for a while now in the Fedora community. But if you really look into it, my personal opinion is that Ubuntu's stance on free and open software and open source software is not as strong as a lot of other distributions, right? So Fedora has a very, very clear stance. If it's not free and open source, as an example, if your tool is open source, but you add a clause that says it cannot be used commercially, that's not good enough for us, right? Free and open source means accessible to everyone. We will not negotiate on that front at all. So one is the philosophy of the community. And the second, of course, is that while Ubuntu may be good, I know it's been called Linux for humans, but as you can clearly see, the other distributions are not much different in that aspect. The other advantage, as I briefly noticed, observed, was that Fedora becomes part of the full RPM ecosystem. So all the work we do for Fedora trickles down to CentOS, Scientific Linux, and Red Hat Enterprise Linux. So when I have Nest on Fedora, I can now also very easily use the same package and make it available on a supercomputing platform that may be running some variant of CentOS or Red Hat Enterprise Linux, right? Yeah. So I mean, it's a mix of a bit of history and personal opinion, of course. But yeah, but I know the prevalent view seems to be that Ubuntu is much easier to use. That's not really true. It's generally because it's so well marketed and they say Linux for humans and so on that everybody tends to start with them. But if you look at Fedora or SUSE or even Debian, which is slightly more technical, the usability factor comes pretty much from the interface, and all of them use the standard GNOME interface, right? So It's not any harder nowadays. So basically people are spoiled for choice. And if they want to use a lot of the tools we make available, then please come to Fedora.
Yeah, I think there's a question in the chat.
Yes, you can use not Fedora, the operating system, but the container image with all the software we have on any operating system that supports containers. So as long as you have Docker or Podman installed, you can use it anywhere. You can even use it on Windows, but the last time I tried to set up Docker in Windows, it was a nightmare. I can't speak for that at the moment.
I think they improved on that. So I had a second question. I understand you're tied to the Fedora ecosystem, and I don't disagree. I used RPM for a long time. I know them very well, but at the same time, like if you look at any of the Docker images today, like everyone starts with an Ubuntu image. Ubuntu that's
primarily because Travis started with Ubuntu.
Right.
And so that in a weird way, that's become an ecosystem now, because if people use Travis, they get an Ubuntu.
Right.
I think some of that comes from Ubuntu providing an LTS, a long-term.
Right. Right. But anyway, yeah, so I understand. But so then there was another distribution called NeuroDebian a couple of years ago.
Yeah.
I forgot which school it's from, but they were more like neuroimaging focused.
Yeah.
So you guys collaborate or something? Was there any?
No, because I mean, so a lot of the packages we have are inspired by NeuroDebian, but as you noticed, yes, they are more of a neuroimaging community. And there again, so Debian and Fedora communities differ in philosophies, and we differ in how strict we are with software practices. So when something is included in Fedora, we have a very strict checklist that must be followed. And it's not limited to licensing. It's things like, have all unit tests been run? Do all of them pass? Are C++ coding guidelines followed? So on and so forth. Debian's has similar guidelines, but they're slightly more relaxed. But when it comes to scientific software, correctness is very, very important. And therefore, yeah, personally, I need to make sure that all of these tests have been run, because if somebody uses Neurofedora, they publish a paper and it turns out that there was a bug in our build because we didn't do something right, then some of these scientific results will be affected. Right. So I mean, with Linux distributions, a lot of this comes down to personal preference, really. And because we managed to organize around Fedora and with Red Hat's backing and so on, we've just down this path. But yeah, NeuroDebian is an excellent operating system. I have used it myself for certain tools. So if that fits somebody's use case better, please go ahead and use that. Yeah.
So I know Anka is going to kill us because we're over time. So I just want to finish by giving a thumbs up to Neurofedora, because I recently downloaded it and installed it, and it was working fine. So we had a good use
Great.
of it.
Thank you very much. It's always great when people use it and we get good feedback. Thank you.
Yes, I am going to cut it here, and I will invite everyone to keep the discussion going on Discord channel. Our channel is Showcases, or on Tutorials General. Thank you, Ankur, for a very nice introduction to CompNeuroFedora. And now it is my pleasure to say good morning. Australia is 4th of July over there. And invite on the screen our next speaker. Our next set of speakers are coming from Australia. So 1 second. All right. So I'm inviting Dr. Stewart Hyman all the way from Australia, and he is going to talk about the Brain Dynamics Toolbox. Okay, we have a little delay in here. Hello, Stewart.
Hi, Anka. Sorry, there was some delay for some reason.
Yeah, good morning.
Good morning. Sunday morning here, and we're all in lockdown.
Oh, really?
Well, Sydney is, yep.
So nothing else to do. What else is better than CNS, right?
That's right. What a great way to spend lockdown.
Yes. You have the microphone.
Okay, so how do I share my screen here? Share screen. Entire screen. Allow.
It's coming. Yes,
Okay.
I see it.
Click to close message. All right, so you can see everything infinitely. All right. Okay. Now, can you see my mouse, Anka?
Yes, we do.
All right. Okay, so I'm in full screen, so I can't see the chats. So, Anka, perhaps if chats pop up, you can just tell me about them. Anyway, so I'm here. I'm from the Victor Chang Cardiac Research Institute, and I'm describing the Brain Dynamics Toolbox today. So the Brain Dynamics Toolbox is aimed at the type of problem which I think most people in this forum will have faced. And that is basically when you're writing your own scripts for your custom simulations, you might have found yourself in a situation where you're continually editing out parameters in your own code, plotting the results by hand, and you might have wished, gee, wouldn't it be great if I could have a graphical user interface where all I have to do is change the parameters on the fly and instantly get a visualization of my simulation outputs. So that's what the Brain Dynamics Toolbox is. It's a MATLAB toolbox for simulating user-defined differential equations. So the focus is on on the equations. The philosophy of the toolbox is that you, the researcher, should have full control over your equations that you wish to model, but you don't necessarily wish to be burdened with the graphical programming effort to visualize them or make these sorts of graphical interfaces. So with the equations, the toolbox supports the three major classes of differential equations that you typically find in computational neuroscience. So these include ordinary differential equations, delay differential equations, where you might be interested in transmission delays, for example, and stochastic differential equations, where you might wish to add some independent noise sources to your model. And each of these three classes of differential equations can be extended in space by casting them as a system of partial differential equations using the method of lines. So here's a quick example of a partial differential equation running in the Toolbox graphical interface. So what you're seeing here is 100 by 100 Fitsu Nagumo cells arranged in a sheet, and this particular simulation is representing arrhythmogenesis in a sheet of cardiac tissue. So how does it all work? As I said before, the toolbox has this philosophy of being equation-centric, and you can think of the toolbox as a hub which connects your models, your equations, with the existing solvers in MATLAB, the numerical solvers, and also the existing display panels with the Brain Dynamics Toolbox. So the idea is that you provide your models, you retain full control over them. By models, I mean equations, and but you're not bothered by calling the solver or displaying the output. The toolbox takes care of all of that on your behalf. So now it does have a modular design. So if you wanted to, you could also code up and include your own solvers, and you can also write your own display panels. So you're not boxed in by the system. You can extend it to fulfill your particular needs. So what's a model look like? Here is an example of a user-defined script that populates a data structure called SIS. This is a network of Hindmarsh-Rose neurons. It takes a single input parameter, which is the connectivity matrix of the network you wish to define, and it populates a system structure which you then load into the toolbox to run. I won't go through all the details here, except just to highlight the core function of this script is the ODE function. This one here from line 72 to 89. So if you're familiar with calling the MATLAB ODE solvers manually, you should recognize the format of this function immediately. It's the same format. But I don't want to go into the detail of the programming here. Really what I want to just emphasize here is this script is less than 100 lines long. And that's fairly typical for most models in the Brain Dynamics toolbox. I have been chided for saying it's only 100 lines long. Some people have said, don't say that, people will freak out. But really, 100 lines is not very much. And if you're in the business of computational neuroscience, I think you'll be used to doing some programming. But even so, with just 100 lines, you do get quite a rich graphical interface from that. So this example I'm showing here in the corner is the graphical interface for this particular Hindmarsh-Rose neural model. And you can see you have time portraits, face portraits, space-time plots, Hilbert phase plots, and you can load more panels on the fly if you wish to do that. Now, the best place to start with the toolbox is with the example models. It ships with 30 or more example models, and you can view a gallery of models on the BD Toolbox website as well. The models are listed in the handbook for the Brain Dynamics Toolbox in Chapter 1, and you can download Chapter 1 from the bdtoolbox.org website as well. So rather than trying to describe the toolbox, what I'm going to do now is just switch over and show you some examples of how you can use it, and I think you'll get the idea of how it might benefit you. So we're going to look at the last example on this list here, which is the Wilson-Cowan model. So let me just switch over to MATLAB. Might get rid of that window. That's a bit distracting. All right, so here I am in MATLAB. I've already set up my MATLAB paths to include the toolbox, and I know there's that Wilson-Cowan model. So let's just say start with help Wilson-Cowan, and this gives us our first information about that particular model. It tells us it's a model with two state variables, E and I. The model is actually a neural mass model of two populations of cells, of excitatory cells and inhibitory cells, but let's just run it and see what happens. And this is how you run most models in the toolbox. We start by calling that model-specific script to generate that system structure. That system structure defines the model and has everything within it that you need to run in the GUI. And now I'm going to run the Brain Dynamics GUI. I'm going to pass that system structure to the Brain Dynamics GUI, and I'm also saving a handle to that GUI, and we'll use that handle later on. All right, so here it is. It takes a little while to load up. It does take a little while to load up, but once it's up and running, it's okay. It's running a bit slower than normal because of the teleconferencing. Very slow. I can hear my poor computer starting to scream. Here we go. All right, here it is. So this is the graphical user interface. All right. So as I said before, the Wilson-Cowan model has two state variables, E and I, which represent the mean firing rates of a population of excitatory cells and inhibitory cells. Here are the parameters relating to, I won't go into the model too much. Here the various parameters of the model. You can see the initial conditions E and I here for their state variables, and the parameters are all controlled in this control panel on the right-hand side. I'll just go for a bit of a tour around the graphical interface. We can tab between these various displays and get different views of different aspects of the simulation. And each time I change a tab, I change this menu. So each tab has a tab-specific menu. I can open new tabs, for example. Let's do a time cylinder. And it's taking its sweet time because of all the graphic load. There's our time cylinder. And this plots time for phase variables, for example. I can close that down and so forth. So you get the idea how you can visualize your system from many different viewpoints. So let's consider this parameter here, JE, which is the external current injected to the excitatory cell. So let's inject some current into our excitatory cells by ramping up this JE parameter. And every time you change a parameter in the control panel, the simulator runs and the results are plotted. So the solver is controlled by this panel down the bottom. You can choose many different solvers. Here's the ADE23 solver, for example, and the statistics down the bottom tell you some aspects of the simulation that's just run. If I want to change the length of my simulation, I can do that by unchecking this time domain slider, and these are the start and end times of my simulation. So let's take it out to 1000 milliseconds and it will recompute. There we go. Now, every time you recompute, all panels get updated. So let's see what happens in the phase portrait as I ramp up my JE parameter. Now it helps with the phase portrait to show the vector field and the null lines. And here's where my system starts here, and it converges to this limit cycle as I increase JE. Now, I might not be interested in these transients, so I can use my time slider down the bottom to eliminate some of those transients. Let's take it out to, say, 700. And you can see the transients here. I'll turn off those vector fields, actually. The transients, that light gray, and the steady state is that limit cycle there. Let's get rid of those transients and just leave the steady state. So now, as I increase JE, I can see what's happening to my limit cycle. I can switch to my time portrait to see how it makes sense. And possibly what's more useful here is we can do a bifurcation diagram. So I'm going to pull up a new bifurcation diagram. I'm going to choose JE as my bifurcation parameter. I'm going to turn off those transients, and I'm going to manipulate my JE parameter to build up a bifurcation diagram. Now I can actually do this in a more semi-automated way by using that handle returned by the GUI, which I mentioned before. This allows me to change things in the graphical user interface from the MATLAB command line. So GUI.par for parameters.JE is accessible to the workspace. That's that value there. Now I can put that in a loop if I want to. I can, well, I can just change it. Let's just change it first. GUI.par.JE equals 0. Put JE to 0. There we are. And there's our simulation here with that result. And let's ramp that with a quick loop. So I go for JE equals 0, steps of 0.1 to 5. I assign that value GUI.par.JE equals JE, end. Now, as I loop through these JE parameter values, the system will recompute each time. We can see the time series here, slightly changing. We can see the emergence of that limit cycle in the phase plane. And we can see this building up in our bifurcation diagram. So I hope you're getting the sense at this point that just by using this combination of graphical controls and the workspace interface, you can quickly get a pretty good handle, a pretty good idea of the dynamics of your particular custom system. Here we are building up that bifurcation diagram. I hope you can see that. It is running a bit slower than normal because of all this teleconferencing. Now, there's a bit more I can show you, but I'm starting to run short of time. So I will move on to the third way. So the two ways so far are using the graphical controls, using that workspace interface, but there's also a set of command line tools that ship with the toolbox that don't use the graphics at all. And that's what you use when you're doing your full-scale simulations and parameter sweeps and such. So here's an example of a small script here, 30 lines, uses that same Wilson-Cowan model and does that same sweep I just showed you, but it does it completely using the command line tools. And I'll just run this to show you that in action. Okay, there's that same bifurcation diagram. All right, back to the presentation. So I hope that's given you a sense of how you use this system. The combination, this slide here is just to show those command line tools, which I just demonstrated. And the command line tools really fit in well with the interactive way of working. In fact, the three ways of working with the toolbox really complement the typical life cycle of a research project. So you can imagine that you have your script, your command line script that you work on to do large-scale simulations or large-scale parameter surveys. And perhaps something goes wrong with that script. Something went a bit weird. You want to investigate that more thoroughly. So you can pull open that particular instance of that model in the interactive GUI. You can play around with it there and realize what happens. Say, oh, perhaps I had to change the tolerance of the solver or something. If you want to double check your thinking, you might run a quick and dirty parameter survey using the semi-automated methods in the command line, and then take that fix back to the script and iterate as you go. And of course, the last stage of the research lifecycle is dissemination. So when you've finished with your simulation and you've published your paper, you also want to publish the model that goes with it, or the source code that goes with it. So you will just publish that particular user-defined script that you wrote. And if someone else wants to use it, they'll download the toolbox and use your model to run it. And a good place to disseminate models is Zenodo. There's a community collection for the Brain Dynamics Toolbox on Zenodo. So if you haven't heard of Zenodo, it's an archive quality repository for digital resources. Every resource gets a citable DOI, a digital object identifier. And I think that's a really good way of sharing code with your preprints and your papers. It's not like using GitHub or something where the repository is designed for people working and contributing code. These records in Zenodo are more like snapshots, so they better work with the idea of a published work, a published paper. And because you get that that citable DOI along with your piece of work, it also ensures that the people that write the software get more credit. And it typically happens when people just share their GitHub repositories. But anyway, that's a side issue. If you want to share your code, distribute it with other users, then I encourage you to upload it to Zenodo. Other digital, other online resources that will be of interest to you are the training resources. So if you're new to the Toolbox, you can enroll in the Toolbox Basics course. That's like a 2-hour or less course just to help you get started with installing the Toolbox and running your own models. There's also a more advanced modelers workshop course. It takes you about 8 hours to get through, and that's more about programming your specific models. And of course, there's the handbook for the Brain Dynamics Toolbox, which you can find on the website also. So that wraps up the Toolbox. If you're interested in downloading it, go to bdtoolbox.org. I'm Stewart Hyman, and I just want to acknowledge Michael Breakspear, who's the other project leader for this particular project. So back to you, Anka.
Yes, we do have great toolbox over there. So we have some questions, and I am going to invite them on the screen. So let's see. We have Michael. So let's see if he wants to come on the screen. Seems that there is a little delay. Okay, so he doesn't have the connection. Good. So can you see this the question?
I can see one question that says, "Hi, great tool.
That's
Can the tool provide output for the system, such as allocation of fixed points and bifurcation points?" The answer is yes. With that handle to that graphical user interface, you can access any state in the trajectory. Bifurcation points, it's not a continuation tool like MatCon, so it does not detect bifurcations. It's a forward simulation tool. So manually you can figure out what the bifurcation is, and you can locate that point, but there's no detection, automatic detection. If you're interested in continuation, I suggest you use MatCon or Coco, and MatCon actually in particular has a very similar design system structure, so it works pretty well with my toolbox. Point care maps, no, I don't have those yet, and I don't have Jacobians. You can put Jacobians in your model if you want to, and you can have explicit definitions of those. Hope that answers your question. Next one. Your toolbox looks amazing. I used MATLAB for a long time and simulated neural model ODEs. One problem was how slow it was. Does this limit your toolbox? Speed is MATLAB. Look, I'd say this is not about speed in terms of CPU speed. The simulations can run quite slowly in MATLAB. It's more about the speed of development and getting your program or analyzing your model as quickly as possible. So I'd say with a typical research project, you're often changing your ideas and exploring new things all the time. So in that case, the slow part is the person rather than the machine. So the philosophy there is it's not about CPU speed, it's about convenience.
I agree. I did some modeling in MATLAB too, and for small models, if you're doing like a single cell, some simple equations, usually the speed, it doesn't really matter. But other people like are trying to run like large scale simulations. In those cases, MATLAB is not the way to go. But I guess for these users, for your toolbox, is not really a limitation, right?
Yeah, I think that's right. I mean, if you're really scaling up big time, you're going to reach a limit with this toolbox. This is more about getting intuitive understandings for the dynamics of your system, really. And it's quite a good teaching tool for that matter as well. People using it in their physics classes and dynamical systems classes. It's not just restricted to computational neuroscience.
I saw that your book got some prizes. Is that?
Yes, you have to pay for it.
Cool.
Not everything's free in life.
No, I saw that it won a prize somewhere.
Oh, a prize! I think it's a prize.
Oh.
Yes, a couple of prizes. They won a prize in the Siam Society for Industrial Mathematics a couple of years ago. So yeah, best software tool in the postdoc division, and honorable mention as well. Sorry, I thought you said price.
It's about money.
The toolbox looks great, by the way. Good job. Good work.
But the toolbox itself is free. Don't worry, it's okay. You can download that for free, and you got to pay for MATLAB.
We are in the process of trying to renew our license. It's always a fight with the department to get the money.
Look, a lot of people are against MATLAB because it's expensive. I understand that, well, there's a lot of historical code available, and MATLAB is very hard to beat in terms of getting things up and running quickly. So you might think you're paying money, but you're saving time. So.
Okay, let's thank our speaker. We are a little bit over time, so let's keep the discussion going on Discord, on our channel showcase, okay? Thank you, Stewart. Thank you, Cengiz. So we have a little delay in here, a couple of seconds, until our next speaker, Ben Fulker, all the way from Australia, is coming to talk to us. Hi, Ben. He's going to talk about tools for leveraging feature-based time series analysis to characterize neural dynamics. So, Ben, you have the microphone.
Thank you.
We see your screen. Everything is good.
All right, awesome. Well, thanks, Anka. Thanks, everyone, for joining. Yes, it's early in the morning here in Australia, but it's a nice way to start my Sunday. Okay, so I'm going to talk today quickly about some tools that we've developed for doing feature-based time series analysis, and I'm going to hopefully try and do a quick demo of how you can apply this type of approach to neural time series data. And I'm going to try and leave enough time for questions. So Anka is happy with me. Okay, so here's a typical setting that you might find yourself in. You have modern measures of neural dynamics that are getting very large, and often they're messy. And whether you're measuring EEG, MEG, fMRI, calcium data, you might have a very complex structure in your data set. And the question is, how do I represent all these time series? What methods could I use to try and answer the types of questions that I want to ask of my data? So some typical questions might be, is there any interesting structure there? Are some time series very different to some others? Are they clustering into groups that somehow maps onto the manipulations that I made to test the hypothesis of my experiment? You might want to say, well, what types of properties are distinguishing the classes of dynamics that I've gone and manipulated? So what's different about these neurons compared to these? What's different about this brain area compared to that brain area? What's different when I did this optogenetic manipulation? How do you try and find those time series properties that differ between your classes? And then how accurately can I classify them? If I want to develop a new biomarker for some brain disorder, I might just not really care so much about specific time series properties that differ, but just overall, if I could leverage as many time series properties as I could, how accurately could I distinguish between the different classes in my data? For example, schizophrenia versus control. Okay, so typically to answer a question like this, you have to make subjective choices about time series features that you're going to use to represent your data. And so I'm going to try and talk about that main pipeline and approach, and I'll talk about the tools that we've developed to try and help with this type of question. Okay, so time series are very diverse in the world. What we're going to be talking about in this talk is univariate time series, so repeated measurements of a system over time with a fixed sampling rate. And because there's a fixed sampling rate, you can represent the time series as just an ordered vector of numbers, x1, x2, x3, where it's an assumed constant delta t between those measurements. And we'll be thinking about neural data here, but I'll show some examples of how we can also contextualize patterns in neural data with patterns in other classes of time series data. A big part of what we try and do is focus on the interdisciplinarity of scientific data and also scientific methods. I'll talk a bit about that later. Okay, so this is the kind of foundation of where we're going to take our analysis approach. So we're going to turn our time series data, which could be anything along the left here. These are different time series from different systems. And we're going to turn them into a set of numbers, summary statistics that capture some property about those time series. So whether we use an entropy, whether we use a how big are the outliers, what's the kurtosis of the distribution, what's the autocorrelation at lag 3, how stationary is it, you know, has it got a low attractor dimension or something like this. All of these types of methods we can use to turn a time series into a real number, and that real number is somehow interpretable and maps onto a theoretical literature about dynamics. So what we're going to explore here is, of all the possible ways that I could map a time series to a real number, can I somehow leverage this diversity of scientific approaches to help address a given problem that I want to ask about my time series data set? Okay, so as you may know, there are a large number of possible methods for doing this. People have developed this for decades in many different settings, whether you're in economics and you're trying to forecast forward the inflation rates, or whether you're in astronomy and you're trying to predict what type of star something is from a light curve you've measured from the sky, or you're in applied maths and you've tried to, you know, quantify the fractal dimension of your dynamical system. There are large numbers of possible methods for trying to understand the structure in time series data and for trying to map a time series recording and extract a single real number to capture some structural property in it. Okay, so whenever you try to address this type of problem in practice, you typically subjectively pick a few things that you want to investigate. But the question there is, why not leverage the entire literature on this? And so if it was possible and people had shared all their implementations for all of their scientific methods across disciplines, you could imagine that it would be very quick to share knowledge across disciplines and with other scientists, because this would all be available in one place. And instead of that subjective element, where you never know if the features that you picked were the best, you could actually just apply all the possible methods from across science and see which ones work best on your data, and then go and start looking into that literature to try and understand what's happening in your particular time series data set. Okay, so this is what we call the highly comparative approach to time series analysis. And I'll walk through this with a particular example. Maybe you have two flies here. One of them has a genotype and the other one's a knockout. Some genes being knocked out, and you measure their movement over time as time series of both types of flies. So you have many repeats of this experiment, and you basically want to say, is there something different between these movement dynamics? What is this gene doing to the movement behavior of these flies? Okay, so a subjective approach might go, oh, it seems to be a little bursty here, but we also get a bit of burst there. Maybe we need a burstiness statistic, or maybe I'll look at the Fourier spectrum because I know how to do that, or I'm a wavelet expert, so I'm going to try wavelets. And you could imagine writing lots of small papers, each choosing a method like this. But the approach that we kind of developed is to apply as many methods as possible from across science. So we have this toolkit that implements over 7,000 different time series features. So different properties of their data distribution, different properties of the autocorrelation function and other nonlinear mutual information functions, etc. Different model fits and their parameters, all of those things that I showed on the previous slide. And once we apply all of those, they form columns of this matrix. Right? So each of our time series is a row in this matrix. We've got all of our blue flies and our red flies. And then each of our columns is an interpretable time series property, where I've applied some method from science to the time series and seen whether what sort of value it came out. And then if I want to say which features best discriminate those two classes, I can pull out from all of these different scientific algorithms which features best distinguished. And in this case, it might be some measure of entropy, and then I can interpret, the blue flies have a more disordered movement pattern than the knockout flies, something like this. And I can also do a low-dimensional structure by leveraging all of these different properties together and mapping all of my time series data set into a low-dimensional space. Can I try and understand the structure in the data set? For example, are my knockout flies all clustered in a corner relative to all my normal types of flies? Okay, so this is the approach. Instead of hand-picking features, we can apply thousands of features and then use the data to tell us which types of features are appropriate for solving our problem. Okay, so the tools that we've developed are here. This all started with highly comparative time series analysis, HCTSA, which is in MATLAB, closed and commercial closed source, as we've been hearing about. So this is what computes these over 7,000 features. And on top of computing all those features, it also has analytic functions and visualization for looking at low-dimensional projections, finding the best features, classifying your data. All of that functionality is there. Since then, we've been working on a lot of other open tools, more open tools. I mean, this is free, but it does require a MATLAB license. But we have Catch-22, which we took the best 22 features of these 7,000, the things that we think represent the diversity in scientific time series analysis literature, and perform best on a wide range of classification problems. We coded it in C, and now there's native versions in R, Julia, and wrappers for other languages there. So you can get up and running. This runs really quickly, milliseconds typically, and you can run a large time series data set through Catch-22 very quickly and start getting interesting visualizations and understanding. So I'll show you a Catch-22 analysis, hopefully if we have time with the demo. We've also built a way for scientists to compare their time series data. This is called CompEngine, where you can drag your time series data set onto this portal, and it will pull up similar types of time series data from across science. So I might have time to demo that, maybe not. And then I've got some students now who are developing extensions to this. So Theft kind of does what HCTSA does, but with open feature sets that are available in R and Python, and it will run through similar types of analyses as HCTSA, but in R. You can see that being developed now. There's a web portal that will do that interactively. And we also have a portal for people who've come up with a new time series analysis method and then want to drag it on and see if it's really a new method or whether it reproduces something that's been done before. This compares it to all 7,000 existing features and pops up and says, is your method really novel, or does it actually reproduce the behavior of something that's already been done? And then Oliver, who will speak next, by the way, is developing an extension to this approach to multivariate time series data sets. Okay, so the first thing that you might want to ask from this approach is, how are my time series data structured? So here you might have your two classes of data. You do a dimensionality reduction like I showed you before. And people have done this a fair bit. Well, many of them are us, but okay. So these are all ones that we've done. So this is flies, more flies. This is chemogenetic manipulations in mouse fMRI. This is in astrophysics. This is an EEG data set. These are some leaves in Sweden. If there's anyone from Sweden watching, I've analyzed some leaves from your home country. And you can see that it kind of puts different classes of data in different parts of the space, because this low dimensional projection puts points close in the space that have similar types of features, and not just similar types of hand-picked features, but similar features across a really broad barcode of 7,000 different properties. Another thing you might want to do is classify. So if I can use not just my hand-picked features of 3 or 4 things I came up with, but 7,000 different features, how well can I classify different types of time series? Okay, so we've done this to say here's speech from someone with Parkinson's disease and speech from a healthy control. These are German actors repeating the same phrase in different different anger or happiness or different moods. Should I intervene during labor from the this fetal heart rate monitor? So I've done heaps of things about leveraging a really broad range of time series analysis methods, and other people have done this as well, whether it's looking at how stress affects astrocytes, or what's this one? Another one with stress on neurons, hand gestures, etc. Okay, so just having 7,000 different time series features at your fingertips turns out to be, you can do a lot of useful things with it, rather than having to come up with those features from scratch subjectively every time. So the first thing I'll show is this Comp Engine tool. So this is something we developed to ask, are other scientists studying similar data to me? And so you can drag on your time series. It computes properties of that time series, and you can represent that as a little barcode. And then it tries to find other time series from across science that have a similar barcode. So they have similar types of properties as your data. And then you can look at those neighbors and those neighbors and those neighbors and keep trying to find, explore the kind of wealth of time series across science. So we think this is good because it connects scientists through their data, and it encourages people to share their data, because when you share your data through this engine, you're getting something out of it yourself. You get more understanding of other scientists that are dealing with similar types of data. And if someone else in the future drags their data on and finds a connection to your data, they might contact you, and kind of connects people through the structure of their data. Okay, so this is the type of visualization you end up getting. As a graph view, you can view the neighbors as a list. You can listen. Every time series is listenable, converts it to audio. This is my favorite feature, even though it's not really scientifically useful. But given time, I might skip that, but I encourage you to have a play with that. Even if you don't have a time series to drag on, you can press the explore mode and just look through the whole tool. All of these time series you can zoom in on, move around. All these graphs are interactive, and you might just be curious to browse by category, find the category of time series that you're interested in, listen to them, find their neighbors, and you can download any data that's on the website. You can download all the data on a given page. You can download the whole library. So it's also good for people developing time series analysis methods to see how well they perform on different classes of data, because all of that wide variety of scientific data is available to you. Okay, so in terms of doing an application, I kind of wanted to show you a quick demo of what HCTSA can do. So it can turn your time series, your raw time series data set like this of EEG recordings across different conditions, 5 different conditions in this case. Eyes open, eyes closed, seizure, and then 2 locations in the brain not during a seizure. And it can turn it into this low dimensional projection of your data. So what it's done in the middle is it's computed many features. So in the Catch-22 case, this is the open source fast C-coded 22 features. It's computed those 22 features and then projected down to two-dimensional space. And then you can interact with your data set in this two-dimensional space. Okay, so maybe I'll show you some steps of how you can do that. I might need to share again. I'll share my whole screen maybe. Okay. Can everyone see my whole screen? Yes. How do I know? Yes. You are screen sharing. Okay, that's got to be yes. All right, so I wouldn't know if this isn't working, but I hope it is working. Okay, so what we have is this data set here, where I've just got my 500 time series, each with 500 labels and 500 keywords. For example, the keywords just have 100 labels for each of the 100 time series. My time series data, time series data, just have this 4,000 long vector for each time series. Okay, so the first thing I can do is initialize my analysis with this input file, and I'm going to say I want to compute the catch-22 features for this data set. So it will say you've got 500 time series, 22 pieces of code to run, and it produces this hctsa.mat file. Okay, so this is going to have now a time series table. Maybe I'll just show the first 10 rows. And you can see it's named all the time series, got their keywords in, and the data's sitting there. And if I look at what's called the operations table, that gives me my 22 features here that each have keywords from the catch-22 feature set. Okay, so now if I compute all the features, I'm going to say false because I don't want it to parallelize. It's going to run through, and it's so far, so it takes some amount of milliseconds, so about 0.1 second per 4,000 long time series. So it means we can get through all 500 time series fairly easily. Yeah, so while we're waiting for it to compute, I'll just mention that all of this has a lot of documentation. There's about very comprehensive documentation, lots of tutorials you can do on the HCTSA GitHub site. And there's also a wiki that keeps track of related time series resources, publications that have used this approach, and other data sets that you can download and get started with. So this is just a quick demo of the type of thing you could do. And now if I label the 5 groups, I just run ts label groups. So the next step is just to normalize my features. So all 22 features are on different scales. I want to normalize them all to the unit interval. I can just run ts normalize, and that'll also filter out any bad features. But in this case, all 22 features ran well. And so it's kept all my data and all my features. And now I can plot my low dim representation, and I can pick a dimensionality reduction method there. Okay, so there's my low dimensional projection, and I can now look at, just by clicking through the plot, I can see which bits of data are similar to other bits of data. So here I can see these seizures that are super periodic are up in their own little area here, whereas this seizure is a bit more similar to these types of time series. And you can visually see that this seizure is a little bit different, and it's more similar to this eyes closed time series. Right? This seizure is really quite different. It's sitting down there. So I can immediately start to see the structure in my data, especially when I've colored them by the label that they came from. So that's one of many analyses that you can do with HCTSA. And you can see how quickly you can get to an analysis like this. If I'd have run the full 7,000 features, this wouldn't have happened so quickly. But because of the catch-22 and the 22 features that run in, So quickly I computed their 500 time series that were each about 4,000 samples long, just in a matter of seconds. Okay, so maybe I continue with this full screen mode. Hopefully I've not just been on mute or something. Okay, let me just double check. Okay, people are actually there. Yeah, okay. Okay, Namka's trying to rush me. Okay, so that's this type of analysis. And as I mentioned, there's full documentation. You can work through many other analyses with this data set on this GitHub page. I'm sure there will be a place for me to put these slides up after the talk. And for people interested in R, we're moving all of this through to R, and there's also some Python tools to be done. And if you're interested, here's a set of references. This stuff's been worked on by a bunch of people in our group, listed here. And also historically, this was worked together with these three at Imperial College. Okay, so thanks for your attention. I have a few minutes for questions.
So thank you for the talk. Very interesting, analyzing time series. We have a bunch of questions from Jim Bauer. Jim, I'm going to invite you on the screen if you want to come and ask the questions.
Or I can just pick up the
It takes
gist.
a couple of seconds. It's
Okay.
It's okay. So let's see. Maybe he is coming, maybe not. It takes usually, yeah, here he
there he
is. We see you, Jim. We are good.
Here I am. Thank
Hi,
you.
Jim.
So, the big question is, if you now have access to thousands potentially of different ways to analyze sequences of data, okay, what are there specific examples besides saying sort of this looks like that, where, especially if you're comparing data across a very wide range of systems, from birdsong to whale to, you know, disturbances in buildings because of bad engineering that might lead to their collapse, for example.
Yes.
What do you actually, are there examples of what you actually have learned by making that comparison? So presumably, if there's a high similarity in the data, there may be some underlying structure that's similar or reveals something about the system, right?
Yeah, so there's two things, which is comparing the methods to each other and comparing the data to each other. Your question here seems to be more about comparing the data to each other. And comparing data generically, so I say generically because we're using just a generic set of features. If you wanted to make specific inferences, you know, like which types of data share nonlinear properties, you could pick a different set of features to try and find nearest neighbors in that space. But in the generic space, we tend to find the most interesting connections when you have real empirical data matching with model-generated data.
Right.
So we found, you know, a lot of financial time series were sitting really close to all these stochastic differential equations that had been used to model financial data. All the rainfall was sitting next to the kind of Weibull distributed models that were used to model rainfall. And so we're finding these types of connections that are kind of interpretable. And when you look at all the types of chaotic maps, they were kind of all clustering in a sensible way with each other according to the types of properties of, you know, are they chaotic or are they sitting right before a bifurcation? Or so we're kind of getting some sensible clustering just with this generic feature set. But in terms of real world, yeah, it can be it's more just maybe fun, in that sometimes we'll see that someone's studying space data that has a very specific structure and that matches with some audio data that has a similar type of structure. And, you know, I haven't got a good example of where we've gone, oh, this means that maybe there's a similar underlying generative mechanism, but Yeah.
So can I ask one more question? Is that okay? That's a follow-on. Is that all right?
Anchor permitting.
I don't.
Yeah, Anchor's nodding. Go ahead.
Good. So, okay, for years, I've argued that, if you look at spike train data in neurons, what you basically find is something that looks stochastic, right? Which has always been interpreted, basically, for years and years and years, is interpreted as the nervous system is noisy. Okay?
Right.
So, and there are noisy things out there that produce stochastic data, right? But if you consider the nervous system as an information processing device, and it turns out that Shannon, among others, pointed out that if you want to design an optimal communication channel, that the actual signal should look as stochastic as possible.
Mm.
All right? Because that turns out to mean you're using the full communication bandwidth of the channel. Okay? So here's a case where if you look at a whole bunch of neuronal spike train data and it turns out to be stochastic, right? Looking like noise, looking like white noise, let's say, or noise filtered through something. And then you find something somewhere else in your data set that also has a similar property. Okay. In one case, it may be that actually the non-neural case, it may be that you're actually looking at a process which is in fact stochastic and noisy. Whereas in the neural case, you might actually be looking at a system that is, has evolved to be extremely efficient in its data. And in comparing those two, okay, just at the level of the spike train analysis or of the timing analysis of the events, it would look like the same thing. But functionally, if we're right, or if I'm right about how the nervous system is working at this extreme level of efficiency, which means it's approaching sort of, Shannon's ideas about entropy, et cetera, okay, then there's a very different process underlying it. So that's the question. And is there a way, it seems to me there's a danger, right? Which is the danger you've seen in neuroscience for many years of people just saying, well, here's the spike train distributions, it's noisy, the nervous system is noisy. And by the way, we have lots of systems that can generate noise just like that. There's a danger to sort of miss a big, important functional point by just comparing data.
I understand what you're saying. I think you could never do this data-driven because it only has access to the time series and their properties. So it would only be able to say these two things have similar statistical properties and these are the properties that are similar. It's then up to the scientist to not fall into that trap of over-interpreting the function. So it's just a tool to find connections and tell you what those connections are. Then the burden's on the scientist to correctly interpret that pattern.
Great. So then the last point, which is the last question I asked in my series, and you actually just mentioned a minute ago, it seems to me the real power in this is comparing real data, experimental data, to data generated by models. And there's an enormous problem in that business in neuroscience for many years because people cherry pick the analysis that they're going to do on the data to make their models look as good as possible. So that's just how it works. It shouldn't be how it works. That's how it works. So the question is, this toolkit that you're building could be extremely valuable as a way to actually have a rigorous comparison, be able to say two things. One, if you look at the data this way, it turns out the model's replicating pretty well. But if you look at it across 7,000 different ways to look at it, there's this, which is probably a very important, we know from previous studies, is a really important aspect about how nervous system signals work. And that one, the model can not do at all. So what kind of tools are you building to support this comparison of experimental and model data especially with respect, for example, to parameter searching in models?
Yeah, I think it's a good point that people will. You have the choice to pick an optimistic or a kind of flattering comparison, and if you instead take this approach, going, okay, what are the strengths of our models and what are the weaknesses? You can do this in a data-driven way now, because you can say, well, it's doing well at capturing these types of properties, but we still have work to do capturing these. And I think that's a good way to actually push the field forward, because it highlights the things that we're not yet able to reproduce in our models and says, well, don't worry about these things. We're capturing those thousands of things really well. But this type of other types of properties in the time series dynamics, we're really not doing well. We should focus the field towards that direction.
Perfect.
So I think they can already use our tools to do that.
So are you talking to the neuron people or to the
no,
other people that have neuromodeling? I have one, but anyway, have you talked to them?
No, I haven't talked to them.
Well, you were at the CNS meeting, and I think we're having and we're in Germany, right? So we're having a beer fest 2 nights from now, I believe, at some pub. And maybe we should all get together and talk about it. Oh, no, wait a minute. Wait a minute. We're not doing that.
We are not in Germany.
Maybe next time.
But you should reach out to them, because I think, you know, one of the biggest problems with computational neuroscience for many, many years, in my view, is that we're not particularly sophisticated or careful enough or skeptical enough in comparing modeling to experimental data. And these kinds of tools could actually help us in our skepticism.
Yeah, I'd be happy to chat. Thanks, Jim.
Good. Yep.
Thank you, Jim. We have one question in the chat, and I am going to allow it, but very quickly.
Oh, you're being very generous, Anka.
We are approaching the end, so we have a little bit of time leverage, right?
Okay. I'm happy to, yeah. Are you going to get Jessica on stage, or should I?
Yeah, it takes a couple of seconds. Jessica? Let's see if she's coming. Meanwhile, Cengiz makes a pun. He is awake.
Still awake.
I think she is not able
the
to
good thing
connect.
about online conferences is introverts can just type their questions. Oh, no, okay. They still want to.
Hi. I guess it works. Sorry, I'm cooking dinner in the background. So this is a very cool toolbox.
Anka wants to know what you're
Dal.
talking.
Yeah, some Indian food. But anyway, so I was curious about how this toolbox applies to fMRI data. So often you have many voxels across time, and you can either average the signal across a particular region of interest, or you can look at the signal in every voxel. And those two approaches have sort of different pros and cons. So I was just sort of curious if you could talk about different things people have tried and what might be the trade-offs of those approaches.
Yeah, so we've done a few fMRI studies with this. We've only done it at the parcel level with HCTSA because of the computational burden. It does take a while to compute 7,000 different things, and doing that at the voxel level where there are tens of thousands of voxels would be slow, but it would be possible with a smaller time series feature set like Catch-22. And we've also got a new, so in development that I didn't show it, an fMRI-based C-coded feature set called Catch a Mouse 16, and they were the 16 features that did best at distinguishing DREADS-based manipulation of mouse fMRI. So you could do that at the whole voxel level, but yeah, we've just done it at the parcel level. It turns out that fMRI is quite noisy and typically quite short time series. So a lot of the sophisticated time series analysis methods don't really give you that much extra in that case. It's very hard to find complex nonlinear structure or recurrent structure in something that's kind of approximately a linear stochastic process, at least at the ability to measure it, when you're measuring it so coarsely through time and with such noise and for a short amount of time, even in ways that can be, you know, very head motion corrupted or all these types of issues. So it tends to be a bit overkill to apply HCTSA, I think, in that setting, whereas something like MEG or EEG or calcium, you could really get the high temporal resolution that could justify a lot of these more complex approaches to time series analysis. But yeah,
I was actually wondering if it could like differentiate artifacts well or something.
Yeah, this is something we haven't tried actually, but there are a couple of papers that have done this HCTSA to fMRI mouse, and we've got 2 human papers. So if you check the wiki on HCTSA, you can see some of the work we've done, and I'll be happy to chat more by email or if you have specific questions.
Sounds good. Thank you.
All right. Enjoy your DAL.
Yes. Thank you, Ben. Please keep the conversation going on our channel. We do have a chat channel, so you can chat live actually on Discord on our showcase channel. So now I am going to invite our last speaker on the screen. Thank you, Ben. Okay, so our last speaker of the night, also from Australia, good morning. It's Oliver Cleave. Yes. Hi. I'm going to just go ahead and give you the microphone because we are a little bit late.
Okay, sure. I'll just share the screen. Is that all good? Okay. Hey everyone, I hope I'm still talking and audible because I don't really get any feedback with this system. I'll try and power through. So today is going to be a kind of software tutorial and an interactive session talking about autocorrelation in time series analysis, particularly when we're dealing with linear dependence measures. So things like Pearson correlation, mutual information, Granger causality. We're talking about how to correctly apply these measures and test for their significance. So in particular, I've got a kind of cool example with functional connectivity analysis towards the end there. For anyone who wants to play along at home, I've just added a this interactive script that I'm going to go through on my GitHub page. So all you need to do is go to the GitHub address here and then clone the repository, and you should be able to go to this demos folder here. So yeah, well, the kind of general overview of this tutorial is going to be kind of talking about what autocorrelation-induced bias is, with some simple synthetic examples and AL1 processes, as well as some fMRI data, kind of showing that we can prove that telepathy exists between subjects just by looking at their fMRI data and using some dodgy statistics. Then I'll introduce our theory of modified hypothesis tests and how you can get these hypothesis tests for a whole lot of linear dependence measures, like I mentioned before: Pearson correlation, partial correlation, mutual information, and Granger causality. But I would highly recommend using our toolkit for these, like using these hypothesis tests, particularly for these multivariate measures like mutual information with linear Gaussian estimators and Granger causality, because we provide hypothesis tests for multivariate time series data, and it gets quite involved. So yeah, hopefully our toolkit will be quite useful for correctly assessing the dependence between time series there. And finally, I'll end with a example, like I mentioned before, on constructing functional connectivity matrices and testing which of these edges in the functional connectivity matrix are actually significant based on our modified hypothesis tests. And this is the first time that I've actually done this example, and I found some pretty cool results today. So I'll run you through those at the end there. So if you have the script, I've already run this little warm-up session, but effectively all it does is download some HCP data that we'll be using later on. So I'd recommend running this first. By the way, if anyone's never seen this interactive shell before, all it really does is it's got these little sections that we can run through one at a time. So it's kind of like an IPython notebook if you've ever seen those before. But this warm-up little section, all it does is just get rid of some annoying warnings that I've seen before and add our path. Make sure you add path with this genpath command. So this is the repository path. Genpath will just add everything within that directory and then download the HCP data, which I already have. So it's telling me it already exists. Ignore this seeding of the random number generator. That was just to cheat a little bit so that my examples look a little bit cooler, but they'll work with any of this seeding. All right, so let's get started. So the first little section here is just to get a bit of an intuition as to some of the plots that I'll be showing later on to show what autocorrelation-induced bias is and how to fix it and what we should be seeing with our p-values and our statistics. So the little example here is just showing what you should get when you do a Pearson correlation between two independent observations. So you'd have to hope that when you do a Pearson correlation between two independent observations that you see no correlation. But what happens is because we have statistics, real data, you see some variance of that correlation. So it should be zero, but it's actually slightly not zero. So when we run this correlation function, which hopefully everyone is a bit familiar with from MATLAB, we get the correlation here in R and the p-value here is the second argument. So we can generate this standard normal X and Y processes. They're going to look like this, kind of just noise. Hopefully everyone's a bit familiar with. I decided to run 256 observations, or sample 256 observations from this node just because. And I get a correlation of minus 0.04, which gives a p-value of 0.5. And then, so what do we normally do with that p-value is test it for significance. So you set a certain alpha, certain statistical significance threshold, and that will decide whether or not your correlation is statistically significant. So I've got my alpha here, 0.2, and I got my p-value here, 0.5-ish. And as I run these, you can see that I'm generating a CDF of p-values there. So my next p-value was 0.772, which went up here. That's still not statistically significant at 0.2. As I keep running these, I might get more and more p-values, which I expect to kind of go along this dashed line here. And then on the fourth one here, because I knew what my random seed was, I knew that I was going to generate a significant value. So with a correlation of minus 0.09, I got a significant p-value at 0.2. So the proportion of significant correlations at peak of 0.2 now is 0.25. And as I keep running this, that will approach 0.2 because this is the null case. There is no correlation between these two independent time series and everything looks all good. So instead of running this the whole way through, I've just given you a quick script below that runs through a whole lot of different observations, correlates them all, and then gets us this beautiful line here, where at 0.2, the proportion of significant values is 20%. So everything works out there, and that's nice. Statistics works. Nothing's wrong. Perfect. But what happens when we start to move into AR1 processes? So actual time series, which is what a lot of people end up doing. They correlate time series data, use slightly incorrect statistical tests to see, so the exact same statistical test to see whether things are actually correlated. But as we'll see pretty quickly, nothing really works as it did before. So in this script, the idea is to generate AR1 processes. So we've got, if no one's really familiar with this kind of form, then we've got the time, the value at time t is given by the value at time t-1 multiplied by a scalar value, and then just a little bit of noise added in. So it's just this autoregressive based on the previous time step. So this code just simply generates these time series here. You can see that this form is exactly the same as the equations up here. And I've given some little modifying, I don't know what these are called in MATLAB's interactive script, but kind of editable functions here. So we're going to generate an autoregressive process with autoregressive parameter of 0.7 and 0.8. And when we do that, you can see that these time series are a little bit more autocorrelated. So they're kind of slowly moving, more so than the previous ones that we saw up here. Much more noisy, much more high frequency. So when we correlate these in exactly the same way as before, we start to build this CDF as well. And let's just see what happens. So this is just using the same MATLAB core function as we did before. You can see it on line 102 there. So as we start to build this, you can kind of see that the line, the curve of the CDF is a lot higher than before. Really just sitting up the top here. And the proportion of significant values of 0.2 is already at 0.65. So what happens when we run it over our 1,000 experiments? Well, we end up with this quite concerning CDF, the p-values. So at 0.2 significance, we actually get 47% significant values. So that very much indicates that we were using the wrong statistics here. But I've kind of been just diving right into autoregressive processes and synthetic processes, and I'm aware that this is a computational neuroscience conference, so I should probably bring it back a little bit and talk about neuroscience. But firstly, this issue of seeing the proportion of significant correlations not matching what you expect it to be under the null hypothesis. What does that imply? That implies that a lot of the significant connections that you see in correlating time series or performing Granger causality or mutual information or conditional mutual information, anything that's based off these similar kind of linear associations, you're going to see a lot of false positives. So here we saw 27% more false positives than we expected at the 0.2 level. So if you set your p-value at 0.05, which is your standard kind of threshold, then we don't really know how many false positives we're going to see in any kind of, when we're correlating any kind of time series. So it's important to know that as we go through in our paper, all of these linear dependence measures are biased. Pearson partial canonical correlation, Granger causality, mutual information, conditional mutual information. And importantly, although I use some synthetic examples there, a large amount of neuroscientific data is autocorrelated in a very similar way, but often worse. So some examples of those is the hemodynamic response causing autocorrelation in fMRI, or simply digital filtering induces autocorrelation. Because effectively up here, I just digitally filtered our noise processes. Okay, so one example that I can use is the Human Connectome Project resting state data, which I've downloaded onto my computer here, and you can do through our scripts. And what I want to do is show that you can prove that two random subjects have a telepathic connection through some dodgy statistics like we used above. So what I'll do here is download the data. All I'm doing is normalizing and detrending the multivariate time series. And when we do this, we get these kind of carpet plots or raster plots of each region of the brain versus time. So we get this kind of cool looking raster plots here. There are 333 regions, 600 observations, because I've kind of only cut out the middle set of these observations. You can see here 200 to 800-ish. And there are 199 subjects, but I'm only showing 2 subjects here. The raster plots are both of them. And then what we want to do with that is I want to show for if I grab a random subject in a random region and I correlate, so that we're just going to get one of these regions of one subject, which is this code here, random subject, random region. X is going to be the random region or random subject of the first random region, random subject, and Y is going to be the second random region and random subject, and then correlate these. And if I do this test 300 different times, I get a very similar looking curve to before. So all I did there was grab completely random subjects, imaged at completely different times a day, and the random regions of those subjects, and we get this significant, we get 35% of those correlations are significant, even though we only expected 5%. So concerningly, that either means that our subjects are telepathic time travelers, or we've messed up the statistics in a very similar way to above. And I'm going to bet on the second one there. All right, so how do we go about fixing this? Well, the first thing to note is what the original two-tailed F-test is for correlation. So that's this funky-looking equation over here. It's simply that you get some statistic on the left-hand side based on the correlation, which is this RXY, and that we know that that's distributed according to an F distribution. So I can just replicate this exactly here. Importantly, this F distribution and this statistic is based on the sample size here, T. So if you recall, we had 256 samples. And what I'll do is just generate our time series from before with this 0.7 and 0.8 autoregressive parameters, and just show that I'm not lying. MATLAB's inbuilt p-value is this very low number, and when we generate it using exactly the same equation as up here, then we get the exact same number. So what we use in our toolkit and all the way through our paper is not the sample size from above, not this t value, but an effective sample size from Bartlett's formula. So Bartlett showed back in the 50s and 40s that when your observations are correlated, so dynamically correlated, meaning you have a time series, there are a different number of samples, effective samples, than you actually had originally to compute the statistic. So this very simple formula that he's got up here is based on the autocorrelation function. So the way that you compute the effective sample size is you look at the autocorrelation, which is how correlated the time series is with itself. So this is the time series correlated with lag 1, with lag 2, with lag 3. So you expect this lag 1 autocorrelation to match pretty well our parameters here. Phi x and phi y are our lag 1 autocorrelations, and that's 0.7 and 0.8. So that's nice. And so what we do to compute the effective sample size is just do the product of these over time and then sum the lot of them. So what we ended up with, we originally had 256 samples. Now we end up with 118 samples effectively. And so if we end up changing this to being higher, to have more autocorrelation, then we get this smoother looking signal. And we get even less samples. So one of my favorite parts about this is that if we actually take a negative autocorrelation here and run it, we get this kind of super high frequency as well as this, and we're correlating against the lowest frequency here. Our autocorrelation function kind of jumps up and down like this, and we end up with more effective samples than we originally started with, which is just a pretty much we explore the state space faster is what it comes down to. But I think it's a really interesting and weird kind of consequence of this theorem. All right, so using this effective sample size, we can then use a modified hypothesis test. So the only difference is that we use T, we replace T with number of effective samples, which gives us a different p-value from before. Or instead of going through all this confusing maths, you could simply just use our toolkit. So like before, I did at the start, just add the path to our repository. It's here, and then use our core B function. So the core B function is the Bartlett correlation between X and Y, and then the only difference is going to be the output of the p-value here. So the correlation won't change from before, but the p-value will. So if we revisit the first order AR processes, then we can look at what the original p-value was, which is this yellow line, versus our Bartlett corrected p-value. So modified test p-value. So this will work for a whole lot of different autoregressive parameters, as long as you have enough effective samples. So something like around 50 effective samples will give you a reasonable looking kind of distribution of the p-values here. Okay, and what about when we revisit the telepathy with modified f-tests? Well, hopefully, yeah, there we go. We're sitting pretty nicely along this line, slightly off because we have a fairly low number of we ended up with a fairly low number of effective samples with this test because fMRI data is so autocorrelated. Okay, so this is just using our core B function. But what are the other different linear dependence measures in our toolkit? Well, we've got correlation, Pearson correlation between X and Y here. Correlation matrices. So this is a correlation matrix between for the multivariate time series. So these are just concatenated here. Partial correlation with where I've just generated a random sample multivariate data set. Multivariate mutual information, where X and Y can be any size multivariate time series. Conditional multivariate mutual information, multivariate range of causality, and conditional multivariate range of causality. So I'm not going to have time to go into all of these, but I'll give a quick kind of explanation for what they are here. So like I showed before, we have the modified test for Pearson correlation, and we have a bunch of different options in here. But by default, we use the modified test, but we do optionally have the finite test, which was the F test that I've been going through at the start of this tutorial. There are another few parameters in here in order to potentially smooth out the computing of the autocorrelation function, which are called tapering. So we have a few different tapering methods. For the most part, you won't need to use those. I haven't noticed an enormous difference, but there is a bit of literature on why you should use those. So we've got the Bartlett tapering, Tucky tapering, and Parson tapering. So these will all output ever so slightly different p-values, but they all end up being quite similar, except for the finite one in the end. Okay, so the reason that we have correlation matrices in there rather than just computing your Bartlett corrected correlation for each pair in your multivariate data set is that it's a whole lot faster to cache all of our Bartlett corrections over time. So if I was to iterate through each pair and compute the correlation, Bartlett corrected correlation, then I need to compute each of the autocorrelation functions over and over and over again. Whereas we've given a quick, efficient solution here, which I would recommend using for functional connectivity analysis. So you can see that it's about 40 times faster if I have a 20 large multivariate time series. So we also provide modified test for mutual information. Again, I'd recommend look at our paper to understand how all this comes out of the wash here and from the Bartlett corrections originally. But effectively, mutual information is a function of correlation. So we can wrap our test for mutual information. We can just provide a wrapper for test for correlation through mutual information here. And it's quite a similar format to the Bartlett corrected correlation. So similar to before, you get your statistic out and your p-value as the second argument. With finite tests, so the f-tests or chi-squared tests, but some just variety in there. But most of the time, I would highly recommend using our modified hypothesis test to make sure you're using the correct ones. Similarly, we have multivariate mutual information for multivariate processes. So here, if we use if we're looking at the mutual information between two bivariate processes, I've just got a simple script here that generates some autocorrelated bivariate processes, and then we pass them in as just our two arguments. Similarly, we get the statistic and the p-value out. Finally, the kind of most advanced method that we have in our toolkit is the Granger causality analysis for univariate processes. So Granger causality can come out, is equivalent to conditional mutual information, where you're looking at the past values of X to predict the future values of Y, and you're trying to work out whether or not there is a statistically significant dependence between these. So in order to get the number of past values, P or Q, so P is the past values of the source, and Q is the past values of the target, you want to, there's a few different ways that you can do that. What we do is something called Berg's algorithm. So if you just call multivariate Granger causality by default, our MVGC function, we'll do all the computing for you. You don't need to work out what this P and Q is. And we'll give you the Granger causality. But if you have some reason to fix this P or Q value, there's an optional argument inside of here. So you could choose P1, Q10, things like that. So fix the embedding of one, fix the embedding of the other, and whichever one you don't fix will be automated through Berg's method. Again, like before, we have the finite tests and the asymptotic tests, so f-tests and chi-square tests, as well as our modified tests, which I'd highly recommend using. So finally, we have modified tests for Granger causality with multivariate processes, which is similar to above. All you need to do is pass in your multivariate time series instead. And as you can see, they're relatively quick for computing. This one was using Berg's method, using fixed embedding of P or Q. All right, so now on to the fun case study. I'm aware of the time's gone a bit over now. So what we're going to do in here is look at the correlation matrix of subject 1, which is just this first subject in the HCP data set is completely arbitrary, and look at the correlation matrix. The order that I've chosen here is ordered by Yo modules, which I've just provided inside the toolkit as inside the data folder here. So if you look at the correlation matrix here, it's quite noisy. You can't really see all that much, but you can vaguely pull out these different modules that are pretty commonly seen in fMRI or connectivity analysis. So what happens when we actually threshold these values and set everything that is insignificant to 0 and significant to the original correlation value? Well, I've chosen a Bonferroni correction method, which is like this quite a harsh significance threshold. So what we can see when we use the alpha of, well, you can see it there. It's quite a low threshold. When you use this low threshold, you get a 30% dense matrix just using the original f-test. And then what's quite cool is when we use our core B function. So again, all it does is it looks exactly the same as the original correlation function, but we just add a B at the end there for Bartlett. And we end up with a less than 2% dense matrix. So it really just pulls out these super conservative autocorrelation corrected hypothesis tests. Oh, geez. So yeah, that's the quick run through.
Thank you, Oliver. Since we are over time, I am going to invite people to ask questions on the Discord channel, and I'm going to end our session and our day, our first day of the event. I want to remind everyone before leaving that we have a e-mascot competition going on. Everybody is welcome to participate. Also, our second day of the event starts tomorrow at 8 a.m. New York time with the second keynote speaker, Bill Bialek, at 8 a.m. in the morning. See link on Crowdcast on Shed. And hopefully you had a very nice day today, listening to a lot of good computational neuroscience. And have a wonderful day, evening, and night. And I will see you all tomorrow. Cheers.